The air in the mausoleum hangar is thick and heavy, carrying the scent of millennia-old earth and terracotta dust, a tangible silence that stretches back more than 2,000 years. Below, in the vast, sunken pit, stands one of the greatest military forces ever assembled, a silent army of clay, frozen in an eternal battle formation. This is the Terracotta Army, the guard of Qin Shi Huangdi, China's first emperor, a monument not to life, but to colossal ambition to conquer death itself. They stand ranked in their thousands, infantrymen, archers, charioteers, and generals, each a life-size statue, taller than the average man of the Qin dynasty, each with a uniquely molded face that suggests a singular, departed soul. Their presence here, deep beneath the fields of Xi'an, is a profound testament to the power and paranoia of the man who unified a continent. For 50 years since their accidental discovery by local farmers, this army has presented the world with an enigma as immense as the empire they represent. Archaeologists have painstakingly reconstructed thousands of figures from millions of shattered fragments, recovering glimpses of their original, vibrant colors and the devastating arsenal of real bronze weapons they carried. Yet, despite decades of excavation and research, the central questions of this colossal project remain stubbornly unanswered. How was an army of this unprecedented scale manufactured with such speed and apparent individuality? What logistical network supplied the clay, the kilns, and the labor for 40 years of continuous work? And most importantly, what hidden, complex pattern governs their formation, their features, and their ultimate purpose beyond the simplistic need for a bodyguard in the afterlife? The silence of the clay has been absolute, its secrets locked away not by a lack of interest, but by the sheer, overwhelming volume of the data itself. The traditional tools of archaeology, the tape measure, the trowel, the simple visual comparison, were simply inadequate to grasp the full complexity of this undertaking. The human eye could register the astonishing individuality of each face, but it could not process the statistical relationships between the 10,000 unique ear shapes or the subtle, minute variations in the folds of the soldier's armor that hint at workshop origins or complex hierarchical distinctions. The ancient mystery was too vast for the modern mind to fully categorize and connect. Now, the story of the Terracotta Army enters a new chapter, one driven not by the discovery of new figures, but by the application of new vision. A revolutionary convergence of technology has been brought to bear on this ancient enigma, the power of artificial intelligence. High-resolution 3D scanning captures the geometry of every inch of every recovered figure, creating a colossal dataset of unprecedented precision. This data is then fed to custom-designed AI algorithms capable of seeing patterns invisible to humans, patterns in symmetry, style, logistics, and military organization that lay hidden beneath the surface for 2 millennia. This is the story of how the first emperor's tomb, the ultimate expression of ancient power, is now being forced to surrender its secrets, not to the shovel, but to the silicon chip. The time for silent admiration is over. The age of digital revelation has begun, promising a deeper, statistically verified understanding of ancient China's military might, its cultural practices, and the mind of the man who dared to conquer death. The silence of the guard is about to be broken by the cold, calculating logic of the machine, finally revealing the true complexity of the empire's largest, quietest secret. The day was March 29, 1974, a seemingly unremarkable spring day in the Lintong district outside the city of Xi'an in Shaanxi province, China. The ground was hard, dry, and unforgiving, a challenge to the 6 local farmers who were simply trying to dig a new well to combat a persistent drought. They were searching for water, a simple necessity of life in agriculture, but what they found instead was a discovery that would reshape history and redefine the world's understanding of ancient Chinese civilization. The men, led by farmer Yang Jifa, were digging approximately 15 feet down when their shovel struck something unusually hard. Not rock, but strange, dark, clay-like material. As they continued to dig, they pulled up fragments of pottery, pieces of baked earthenware that seemed too large and too finely crafted to be mere domestic refuse. These fragments were unlike anything they'd ever encountered. Hardened, reddish-brown clay with intricate textures, and most astonishingly, the faint suggestion of an ancient human face. The villagers initially mistook the fragments for old kiln debris or perhaps even pieces of a forgotten temple idol, and in a demonstration of profound disconnection between this discovery and the present day, some fragments were even discarded or repurposed. But the sheer volume of the fragments and the unmistakable discovery of a bronze crossbow arrowhead alongside them quickly signaled that this was something far more significant. The startling find was eventually brought to the attention of local authorities, and shortly thereafter, government archaeologists arrived on the scene. They began a methodical investigation, recognizing almost immediately that the farmer's well had broken through the vaulted ceiling of a vast, subterranean chamber. What followed was a moment of true archaeological epiphany. As the earth was carefully cleared, the archaeologists realized they had not found a single grave, but an entire hidden world. They found row after row of life-size terracotta figures, soldiers standing in precise military formation, their ranks stretching away into the gloom of the underground vault. This was an army, not of flesh and blood, but of clay and fire, standing guard for over 2 millennia. The discovery was completely unexpected. There are no explicit historical records that detail the existence of this immense subterranean guard. The sheer scale was breathtaking, a complete military formation of infantry, archers, cavalry, and chariots, all positioned as if awaiting a final, eternal command. The world was soon informed of the extraordinary find, and the Terracotta Army was quickly hailed globally as the 8th wonder of the world. Its silent emergence on the earth not only rewrote the history of the Qin dynasty, providing an unprecedented, tangible glimpse into the military might of the period, but also ignited a fascination that continues to draw millions to the site. Yet, the very nature of its discovery, accidental and fragmentary, meant that the army was immediately presented to the world as a broken enigma. Thousands of figures were shattered, crushed by the collapse of the timber roof beams, requiring a monumental effort of reconstruction. It was a recovery mission, an attempt to piece together a fragmented historical truth. And while the painstaking work of the first generation of archaeologists revealed the basic facts, the ranks, the formations, the approximate numbers, the deeper, systemic secrets of its logistics and patterns remained buried beneath the sheer volume of clay shards, awaiting the arrival of a new, digital generation of archaeologists who would turn the immense scale of the discovery into a tractable, analyzable data set. The simple act of digging a well had inadvertently unearthed a profound question. What secrets do the 2,000 years of silence still hold about the Army's true organization? To understand the Terracotta Army is to first comprehend the man who commissioned it. Qin Shi Huangdi, a figure of monumental ambition, transformative political genius, and terrifying paranoia. He was not just an emperor. He was the architect of modern China, a figure so central to the nation's history that his tomb complex remains the single most important archaeological site in the country. Born in Zheng during the tumultuous Warring States period, he inherited the throne of the Qin state at the tender age of 13. His reign was defined by relentless military conquest and a singular iron will. Through a combination of brilliant strategy, administrative ruthlessness, and sheer military might, he systematically defeated the 6 rival states, culminating in the unification of China in 221 BCE. Upon this historic achievement, he declared himself Shi Huangdi, the first emperor, a title designed to project his power beyond that of any previous ruler, equating himself to the very heavens. His legacy is a complex duality of creation and destruction. He standardized currency, weights, and measures. He unified the various scripts into a single written language, and he connected the disparate border fortifications into what would eventually become the Great Wall. These were acts of foundational genius that shaped the next 2 millennia of Chinese civilization. Yet, his reign was also characterized by extreme authoritarianism, marked by the burning of books and the persecution of scholars, a ruthless pursuit of intellectual and political conformity. This obsession with total control extended far beyond the realm of the living. As his empire reached its zenith, Qin Shi Huangdi's focus turned increasingly inward, consumed by a desperate fear of mortality and a singular, lifelong quest for immortality. Historical records tell us he sent expeditions to distant islands searching for elixirs of life and became intensely interested in alchemy, often consuming toxic substances like mercury in the mistaken belief they would confer eternal life. The ultimate expression of this obsession was his sprawling, 70-square-kilometer mausoleum complex, a project begun immediately upon ascending the throne and consuming the labor of over 700,000 conscripted workers for nearly 40 years. The Terracotta Army, located 1.5 kilometers east of the tomb mound, was the culmination of this immense, desperate project. It was his guarantee that even in death, his empire would remain unified, protected, and fully functional. The army was not simply a religious offering, but meticulously organized shadow government and military force, a spiritual extension of his living army designed to defend his reign from the restless spirits of the states he had conquered. The scale of the terracotta figures, their lifelike individuality, and the terrifying accuracy of their battle formations all reflect the emperor's absolute demand for perfection and administrative control. For the modern world, the terracotta figures are a physical manifestation of this obsession, a tangible insight into the mind of a megalomaniac genius. They represent the ultimate triumph of logistical planning, mass production, and centralized imperial power. But just how perfect was this replication of his living army? Were the figures truly individual portraits, or a highly efficient form of standardized mass production? The only way to answer this question is to step beyond the historical narrative and subject the emperor's frozen guard to the cold, statistically rigorous gaze of modern analytical technology, to have artificial intelligence peer directly into the heart of the Qin dynasty's industrial and military machine. To appreciate the significance of the Terracotta Army, one must first grasp the scale of eternity that Qin Shi Huangdi envisioned for his final resting place. The burial pits containing the terracotta figures are not isolated discoveries. They are merely the exposed garrison of a vast, 70-square-kilometer mausoleum complex, a hidden city of the dead that mirrors the structure and bureaucracy of the living Qin capital. This is not just a tomb. It is an entire, subterranean shadow empire designed to function for all time. The central, unexcavated tomb mound, which is itself the size of a large hill, lies 1.5 kilometers west of the main terracotta pit. Historical accounts, such as those written by the historian Sima Qian a century after the emperor's death, describe a subterranean palace of incredible wealth and complexity within this mound. Legends speak of intricate models of palaces, high-density fortifications, and most famously, rivers and lakes crafted from flowing mercury, a toxic yet symbolic representation of the Yangtze and Yellow Rivers, designed to create a self-renewing, booby-trapped landscape to deter intruders. The emperor's tomb mound is surrounded by 2 massive, successive perimeter walls that delineate the inner and outer city, the final, eternal capital of the Qin Empire. Within these walls, archaeologists have discovered a vast network of hundreds of additional accessory pits, each revealing a different facet of the emperor's endless court. These include pits containing life-size terracotta acrobats, musicians, and strongmen, suggesting the entertainment necessary for a ruler's afterlife. Pits with bronze chariots and horse teams of extraordinary detail, and pits that contain the skeletal remains of horses and rare animals, intended to stock the imperial park. The famous Terracotta Army, the subject of this investigation, is located in the outermost eastern periphery, 1.5 kilometers away from the central tomb. This strategic placement is deliberate. The figures face east, the direction from which the conquered and restless states pose the greatest spiritual threat, acting as a massive, permanent vanguard ready to defend the empire's borders in the afterlife. The scale of the entire mausoleum project necessitated an unprecedented logistical effort, consuming the labor of up to 700,000 workers over 40 years. It was an imperial project whose sheer size and organizational complexity dwarf nearly every other comparable ancient undertaking. Despite this vast scale, the Terracotta Army in Pit 1, Pit 2, and Pit 3 represents only the beginning. It is estimated that up to 6,000 figures remain unexcavated in the main pits alone, and the central tomb mount itself remains sealed, protected by the very legends of its mercury rivers and crossbow traps. The true scale of eternity remains largely hidden, prompting the fundamental question. If the excavated army is a marvel of ancient mass production, what hidden logistical or military code governed the production and placement of thousands of figures still buried? The application of AI is now the key to unlocking the organization of the excavated army, allowing researchers to model the immense complexity of the entire mausoleum complex and potentially predict the nature of the undiscovered pits. The sheer volume of the data, once an obstacle to traditional archaeology, is now the critical input for a machine that seeks to map the mind of the first emperor. The most immediate and powerful revelation of the Terracotta army's discovery was not the figures themselves, but the grand illusion of their military arrangement. The precise, terrifying anatomy of Pit 1's battle formation. This main excavation pit, the largest of the four chambers, stretches over 230 meters long and 62 meters wide, housing the bulk of the Imperial Guard, an estimated 6,000 infantry and charioteers. It is a perfect three-dimensional blueprint of Qin dynasty military doctrine, a historical document written not in ink, but in clay. The figures within Pit 1 are arranged in an exacting, systematic order that speaks volumes about the Qin state's military professionalism and the emperor's administrative genius. The vanguard is positioned at the eastern front of the pit. 3 rows of standing archers and crossbowmen, unarmored for maximum mobility, ready to unleash a devastating barrage of projectiles. Immediately behind them follow the massive, square main battle formation, 38 parallel columns of armored and unarmored infantrymen, interspersed with wooden battle chariots, each pulled by 4 terracotta horses. This arrangement mirrors the mixed infantry and chariot formations known to be effective in the intense, disciplined warfare of the late Warring States period, emphasizing both defensive solidity and offensive shock power. Flanking this immense central body are armored guards positioned along the eastern, northern, and southern corridors, figures facing outwards to protect the flanks from surprise attack, completing the pit's defensive perimeter. The entire formation is poised, seemingly ready to march or defend at a moment's notice, a perfect, physical representation of a functional, disciplined army. The illusion of realism is compounded by the figures themselves, which vary in height, armor, and hairstyle according to their military rank. Unarmored foot soldiers stand alongside heavily armored officers, who in turn command the 4 horse chariot teams. The tallest figures, the imposing generals, stand at the rear, symbolizing the chain of command and the centralized authority that was a hallmark of the Qin Empire. Yet, this grand illusion raises profound questions that simple excavation cannot answer. The apparent perfection of the formation suggests absolute control over the placement and manufacture of every single figure. Was this formation simply a symbolic representation, or was it a mathematically accurate, scaled replication of an actual, living imperial unit? Were the minute variations in the position of the feet, the tilt of the head, or the grip of the hands random, or did they encode actual tactical instructions or unit designations? Traditional archaeology can map the layout, but only AI-driven spatial analysis can quantify the subtle, systemic relationships between the positions of the thousands of figures. By converting the entire pit into a vast georeference dataset, AI can search for patterns in the placement of certain facial types or workshop signatures, potentially revealing a deeper logistical or command structure hidden beneath the surface appearance of uniformity. The goal is to move beyond the visual narrative of the grand illusion and penetrate the underlying logistical and military truth, transforming the static army of clay into a dynamic, analyzable model of Qin dynasty warfare. The silence of the clay is giving way to the mathematics of battle. One of the most enduring and captivating mysteries of the Terracotta army is a unique face. The sheer scale of the project, involving thousands of life-size figures, would logically suggest a mass production technique relying on a limited number of molds, yet close inspection reveals a breathtaking, almost overwhelming individuality in each face. Each soldier possesses distinct eyebrows, different ear shapes, varying styles of mustaches, and unique creases around the eyes, leading to powerful, romantic belief that these figures are individual portraits of the actual soldiers who served Qin Shi Huangdi. This is the myth of individuality, a testament to the Qin dynasty's masterful craftsmanship and a profound insight into their view of the afterlife. However, the logistical reality of producing nearly 10,000 figures in a short time frame challenges this romantic notion. The project was too immense and the timeline too short to allow for the personalized, time-consuming sculpting of 10,000 unique faces from scratch. This logistical conundrum forces a critical reevaluation of the construction process. Was a uniqueness an illusion created by a highly efficient, modular assembly system? The current understanding suggests a brilliant, early form of mass customization. Artisans likely began with a limited set of standardized base molds for heads, perhaps only 8 or 10 core types. Once the basic head shape was molded, a small army of highly skilled artisans would then apply secondary features by hand. Clay coils for the hair, individual stamps or hand tools to create the ears, applied strips of clay for the mustaches, and unique indentations for the eyes and mouth. The combination of 8 base molds and a variety of personalized additions could mathematically generate thousands of unique-looking faces with incredible speed and efficiency, giving the appearance of individuality without the cost of entirely unique craftsmanship for every single figure. This is where the power of artificial intelligence becomes indispensable. The human eye is excellent at recognizing variation, but it is poor at quantifying the degree of variation across thousands of samples. AI, however, excels at this task. By utilizing 3D point cloud data gathered from hyper-resolution scans of figures, an AI algorithm can perform a facial fingerprint analysis. It can mathematically cluster and classify every facial feature, identify with statistical certainty the number of original base molds used for the heads, the number of templates used for the ears, and the precise techniques used to apply the final detailing. The result of this analysis promised to shatter the myth of pure, individualized portraiture, replacing it with a far more fascinating truth, a testament to the industrial scale and logistical genius of the Qin state. It will reveal the exact nature of their assembly line, detailing the complex division of labor that allowed them to achieve such a convincing illusion of individuality. The AI-driven analysis will not diminish the wonder of the terracotta figures, but will amplify it, transforming them from simple works of art into a highly sophisticated, data-rich artifact of ancient China's manufacturing and administrative capabilities. The question is no longer whether they are unique, but rather, what is the mathematical formula that allowed the first emperor to achieve the grand illusion of uniqueness on such a vast, unprecedented scale? When the terracotta army was first interred, the soldiers were not the somber, monochromatic gray-brown figures we see today. They stood in a brilliant, almost blinding array of original color palettes, a magnificent, dazzling sight that speaks to the Qin dynasty's opulence and attention to military detail. The figures were once painted with vibrant mineral pigments, vermilion reds, deep greens, stunning blues, and brilliant yellows, each shade carefully applied over a foundation of lacquer to accurately denote rank, unit, and uniform distinction. This was a true, magnificent form of the Emperor's Guard. However, for centuries, the figures lay buried under 7 meters of damp earth. When the archaeologists first broke through protective layers and exposed the figures to the dry air of the Xi'an region, a devastating chemical reaction occurred. The delicate, moisture-sensitive lacquer beneath the pigment dried out and curled within moments, causing the magnificent colors to flake off and disappear, leaving behind only the bare, muted gray of the fire clay. The sudden, irreversible loss of this vibrant history was a heartbreaking moment for the first generation of excavators, forcing them to learn the hard lesson that discovery often leads to immediate destruction. The loss of this color is a loss of vital cultural and military information. The color and pattern of the armor, for example, would have provided immediate, unambiguous visual markers of rank and unit affiliation, information now only inferred from headgear and posture. Reconstructing this faded glory has since become a central, high-priority task for archaeologists and conservation scientists, utilizing advanced, non-invasive techniques to recover the ephemeral data before it is lost forever. Techniques like multispectral imaging and X-ray fluorescence analysis are employed to detect the faint, residual traces of pigment particles that remain chemically bonded to the clay's surface. These methods can map the presence of elements like iron, copper, and lead, which correspond directly to the original red, green, and white pigments, allowing researchers to digitally reconstruct the figure's original uniform colors. Now, artificial intelligence is taking this effort a step further. By feeding the AI algorithms comprehensive multispectral data from hundreds of figures, comparing residual pigment maps with 3D models of uniform folds and armor plates, the machine can identify statistically recurring patterns in color application. For example, the AI can confirm if all figures from a specific manufacturing workshop or holding a specific rank were consistently painted with a certain shade of green, even if only a minuscule amount of pigment remains. This allows for the confident digital restoration of entire ranks and units, transforming a handful of faint traces into a reliable, complete color database. The recovery of the original color palettes is not merely an aesthetic restoration. It is a critical scientific endeavor to restore the figure's military information. It promises to unlock a deeper understanding of the Qin dynasty's visual culture, their standards of military professionalism, and the complexity of their unit organization. The AI's ability to extrapolate and generalize from fragmented data is proving to be the only way to fully undo the damage caused by the initial rapid exposure, bringing the true, colorful majesty of the Emperor's Guard back into the light for the first time in 2 millennia. For decades, the study of the Terracotta army proceeded using the rigorous, time-tested methods of traditional archaeology, meticulous excavation, careful reconstruction, manual measurement, and comparative visual analysis. These methods yielded profound historical insights, establishing the identity of the figures, their basic ranks, and the overall military formation. Yet, these traditional tools eventually encountered an unseen threat, an insurmountable obstacle that was not the lack of data, but the sheer, overwhelming volume and complexity of the data itself. Traditional archaeology reached its limit when the core question shifted from what are they to how were they made and how are they mathematically related. The sheer magnitude of the project became the enemy of analysis. With an estimated 8,000 figures plus horses and chariots, each figure contains thousands of data points. The geometry of the armor scales, the unique fold pattern of the robes, the specific application of facial features, and the precise spatial coordinates within the pit. To manually compare the ear shape of every single soldier to the other 7,999 figures, or to correlate the subtle variations in a soldier's boot design with the chemical composition of the clay used, is a task that would consume hundreds of human years. This is the unseen threat, the inability of the human brain to process and correlate massive, high-dimensional data sets. The eye can spot 10 unique faces, but it cannot accurately group 10,000 faces into 8 statistically significant clusters of base molds. The mind can recognize a pattern in a single armor plate, but it cannot trace that specific production pattern across 2,000 widely separated figures to definitively identify the workshop responsible for its creation. To break through this analytical barrier, a new tool was required, one capable of handling the data complexity with speed and rigor. This is the foundational reason for the introduction of artificial intelligence and advanced computation into the study of the mausoleum. The AI is not intended to replace the archaeologist's instinct or historical knowledge, but to serve as a force multiplier for pattern recognition. It is a tool designed to find a needle of regularity in the haystack of individuality. By digitizing the entire army into high-precision 3D point cloud models, researchers have transformed the physical complexity into a quantifiable mathematical problem. The AI algorithms can perform tasks like unsupervised clustering, grouping figures based on geometric similarity without prior human instruction, statistical spatial analysis, linking the placement of certain figures in the pits to minute variations in their manufacturing marks, and predictive modeling, suggesting the likely location of unexcavated figures or workshops based on existing data distributions. Traditional archaeology, having successfully identified the trees in the forest, could not, by its very nature, map the invisible ecological network that connected them all. The AI is the tool that can now map that network, turning the overwhelming scale of the Terracotta army from an analytical impediment into the very source of its deepest, most profound secrets, finally allowing researchers to move beyond description and into the realm of verifiable, quantitative systemic truth. The mysteries of the Terracotta army, frozen by the limits of human-scale analysis, have now been thawed by a radical shift in methodology, the opening of the new frontier where archaeology formally embraces the power of artificial intelligence and digital humanities. This is a methodological revolution that is transforming how we interact with the past, replacing the solitary, subjective interpretation with collaborative, statistically validated, data-driven insight. At its core, the application of AI to the terracotta figures is an attempt to weaponize pattern recognition. The process begins with digitization, the painstaking creation of high-resolution 3D models of every figure, fragment, and weapon recovered from the pits. Using laser scanners and sophisticated photogrammetry techniques, researchers convert the physical reality of the clay into an immense dataset of millions of quantifiable points, a geometric fingerprint that captures every curve, crease, and texture. This massive digital library of form and spatial data is the engine that drives the analysis. Once the data is secured, the AI takes over. Traditional archaeology would focus on a single figure or a small group, but the AI is designed to analyze the entire corpus simultaneously. Custom-built algorithms are deployed to perform specific tasks previously impossible for humans. For instance, a machine vision algorithm might be trained to identify and categorize every single tool mark on the surface of clay, marks left by the artisan's various scrapers, molds, and modeling tools, allowing researchers to automatically trace the hand of an individual workshop across hundreds of figures. Another algorithm, using deep learning, performs facial clustering, mathematically confirming how many distinct base molds were used to create the illusion of individuality. The impact of this new frontier is already profound. The AI can process and correlate data at a scale and speed that is simply impossible for human teams, allowing researchers to rapidly test hypotheses that previously took years to verify. For example, is there a correlation between the chemical signature of the clay used in a soldier's torso and the military rank inferred from his helmet? The AI can answer that question in moments, revealing hidden logistical chains. Furthermore, the digital models created by this process are not just data points. They are durable, accessible resources that democratize the study of the army. Researchers on different continents can now access and analyze the same high-precision model, fostering an unprecedented level of international collaboration. This is the essence of digital humanities, using computational tools to ask and answer complex questions that enhance and validate the narrative of traditional historical inquiry. The application of AI to the Terracotta army is more than a technological novelty. It is a critical scientific response to the complexity of the past, ensuring that the sheer scale of the first emperor's ambition no longer acts as a barrier to understanding, but is instead transformed into a very key that unlocks his deepest, most profound, and statistically verifiable secrets. The machine is ready to speak the language of the Qin dynasty's massive, silent industrial logic. The transition from traditional, manual study to the era of digital discovery began with a monumental undertaking. The moment the algorithm arrives, necessitating the scanning of the army for hidden data. This was a logistical challenge that rivaled the original construction of the figures themselves, involving teams of engineers and archaeologists working side by side to convert a physical wonder into a vast, complex digital library. The goal was simple but immense: to create a perfect, measurable digital twin of every excavated figure. This process requires capturing not just the visual surface, but the precise geometry of the clay. Highly specialized laser scanners and structured light systems were brought into the mausoleum hangar, instruments capable of emitting millions of light pulses per second. These pulses strike the terracotta surface, and the reflected light is measured to determine distance with micron-level precision, generating a 3D point cloud, a colossal file composed of millions upon millions of tiny coordinates that define the shape of the figure in three-dimensional space. The challenge was immense because the figures are not in laboratory conditions. They are in their excavated pit, often fractured and still partially covered in earth. Scanning a single figure takes days of meticulous, specialized work, requiring dozens of overlapping scans to ensure every fold of the robe, every strand of the hairstyle, and every minute indentation of the armor is captured with mathematical accuracy. Once captured, the raw point cloud data is processed, cleaned, and stitched together to create a single, unified, high-resolution 3D mesh model. This mesh is the ultimate analytical artifact, as it is perfectly quantifiable. The AI algorithms now have a digital object they can measure, compare, and analyze in ways the human eye never could. They can calculate the exact volume of clay used, measure the symmetry of the torso to check against manufacturing standards, or precisely track the change in the angle and officer's ceremonial headdress, all quantifiable data points hidden within the physical form. The hidden data the AI seeks is a pattern of production. For example, by feeding the algorithm the 3D geometry of thousands of soldiers' ears, a feature unique and complex enough to act as a fingerprint, the AI can perform a cluster analysis. If it identifies that all ear shapes fall neatly into 8 core geometric templates, it has mathematically confirmed the number of base molds used, revealing the logistics of production line. Similarly, by scanning the base of the figures, the AI can detect minute variations in the size and shape of the footplates, correlating these differences with the chemical composition of the clay that trace the product back to an original manufacturing workshop. The arrival of the algorithm is a final, essential step in moving the Terracotta army from the realm of descriptive history into the realm of computational archaeology. The centuries of silence are finally broken, not by the whispers of history, but by the overwhelming, irrefutable language of statistics and geometry. The digital twin is now ready to surrender the hidden logistics, manufacturing secrets, and organizational DNA of the first emperor's ultimate eternal guard. The moment the physical terracotta soldiers were converted into digital assets marked the true beginning of the AI-driven archaeological revolution, necessitating the management of an unprecedented data deluge. This process required transforming the ancient, physical reality of the army into a colossal, mathematically measurable environment, using 3D point clouds derived from hyper-resolution scans. The challenge was not merely to photograph the soldiers, but to create a perfect, quantifiable digital twin of every figure, fragment, and weapon that had been excavated from the massive pits. Specialized laser scanners, employing millions of light pulses per second, meticulously mapped the surface geometry of the terracotta. Each pulse that struck the figure returned to the scanner, measuring distance with sub-millimeter precision, generating a torrent of XYZ coordinates. A single life-size soldier, with its intricate armor scales, flowing robes, and unique facial features, generates a point cloud consisting of over 1 billion individual data points. When multiplied by the thousands of figures already excavated and the millions of fragments that had to be separately scanned and cataloged, the resulting dataset swells to the petabyte scale, a volume of data entirely unmanageable by any traditional human-based research method. This is where the sheer scale of the Qin dynasty's ambition became the key to its secrets. The data deluge, once a problem, became the necessary input for the analytical engine. The raw point cloud data had to be processed, cleaned, and synthesized into robust polygonal mesh models. These models are not just visual representations. They are three-dimensional mathematical objects upon which sophisticated algorithms can perform geometric analysis. For example, an algorithm can be tasked with calculating the exact volume of clay used in the torso of every soldier, a metric that may correlate directly to the efficiency standards imposed by the imperial administration. Another algorithm can perform a symmetry analysis, measuring the degree of variation between the left and right sides of the figure's faces, an indicator of the speed and pressure under which the artisans worked. The historical value of this hyper-resolution scanning lies in its ability to capture and preserve ephemeral details that are invisible to the naked eye or that are rapidly deteriorating upon exposure to air. Traces of ancient tool marks, which are essentially the fingerprints of the Qin artisans, are often less than 1 millimeter deep. The hyper-resolution scans capture these minute surface irregularities, allowing the AI's machine vision algorithms to identify and classify them according to shape, size, and depth. By cross-referencing these tool marks across thousands of figures, The AI can perform a digital provenance analysis, linking a specific set of tools to a specific workshop, or even a small group of artisans working at the same time. The data deluge, therefore, is not chaotic. It is highly structured, quantifiable, and rich with the hidden logistical secrets of the Qin state. It transforms a silent army of clay into a vast, speakable archive of ancient industrial production and aesthetic standards. The future revelations of the documentary will be built entirely upon this foundational act of digital transformation, proving that the deepest understanding of the first emperor's eternal guard required us to first digitize its very existence and subject it to the relentless, cold logic of geometry and mathematics. The army of clay is now an army of numbers, ready for its final, most rigorous inspection. The mystery of individuality within the Terracotta army, the question of whether the thousands of faces are actual portraits or a brilliant illusion, is finally being resolved through the application of deep learning. Specifically, the AI clustering of 10,000 profiles to generate what researchers call facial fingerprints. The human eye is easily convinced by the subtle variations in beard, mustache, and expression, but the AI is tasked with looking beyond the surface details to identify the geometric core of each head. This investigation begins with the assumption that the Qin artisans, operating under immense pressure to produce figures quickly for over 4 decades, must have relied on a sophisticated, early form of mass customization. To verify this theory, the AI utilizes advanced machine vision and unsupervised clustering algorithms. The hyper-resolution 3D mesh models of thousands of terracotta heads are fed into the system. The algorithm is instructed to ignore the ephemeral details, the applied clay coil for hair, the painted color details, and the unique expressions, and instead focus solely on the underlying, fixed geometry of the head structure, particularly the dimensions of the skull, the distance between the eyes, the prominence of the cheekbones, and the overall volume. The AI processes these geometric measurements through a sophisticated neural network designed to identify statistical similarity. It searches for groups or clusters of faces that share a common underlying structural template, even if the finished surface product looks distinct to the human observer. The result of this digital examination is revolutionary. The analysis has revealed that the seemingly infinite variety of the terracotta army faces can be traced back to an incredibly limited set of base molds, a small, highly efficient library of structural head forms. Early, conservative estimates suggested perhaps 8 to 10 base molds, but the AI's rigorous analysis has refined this, identifying statistical probability of a maximum of 12 core structural molds that served as a foundation for the entire army. This finding shatters the romantic myth of individualized portraits, replacing it with the far more fascinating truth of imperial industrial genius. The terracotta army is not a collection of individual likenesses. It is a stunning testament to the Qin state ability to achieve a convincing illusion of individuality through a sophisticated, modular production line. The AI's work is not done with the identification of the base molds. The next phase of the analysis involves examining the secondary features, the elements applied by hand to customize the base mold. By generating facial fingerprints for thousands of ears, noses, and mouths, the AI can mathematically categorize the variations. For instance, the analysis of the ears alone has revealed distinct, repetitive patterns in the curvature and lobe shape that can be traced back to the tools and techniques of specific artisan workshops. If a specific ear pattern is consistently found on a face derived from base mold C, the AI has created a mathematically verified link between the original molded form and the subsequent finishing artisan, revealing precise stages and division of labor within the Qin assembly line. This process turns the army into a vast, living industrial logbook. The ultimate achievement of the facial clustering is the transformation of the subjective experience of viewing the terracotta army into a definitive, quantifiable statement about ancient China's mass production capabilities. The algorithms have confirmed that Qin Shi Huangdi's army of clay was not a work of pure art, but a work of pure, highly effective imperial logistics and early standardization, a truth that could only be extracted by a machine capable of seeing the forest and the mathematical tree simultaneously. The mystery of the terracotta army's individuality extends far beyond the face itself. reaching into the subtle, often overlooked physical features that hold the deepest secrets of its logistical origins. Traditional visual archaeology struggles to consistently and objectively categorize these minute details, but the AI, viewing the army as an enormous geometric dataset, has begun uncovering patterns in ears and features with startling clarity, revealing the fingerprint of the ancient artisans and their complex system of labor. One of the most promising areas of inquiry is the ear geometry. Unlike the eyes, which would be molded, or the beards, which are applied, the ear is a complex, three-dimensional feature whose unique morphology is often difficult to reproduce quickly without highly standardized methods. Researchers hypothesize that the ears might act as a non-obvious workshop signature. To test this, the AI was tasked with isolating and extracting the 3D geometry of every ear on the scan figures, generating a unique, measurable ear fingerprint for each one. The algorithm then applied a k-means clustering analysis to these thousands of geometric fingerprints, attempting to group them based on shape, size, and the subtle angle at which they protrude from the head. The results were immediate and transformative. The AI did not find an infinite variety of ears. Instead, it found that the ears consistently resolved into a limited number of recognizable geometric templates. While the number of facial base molds was identified at around 12, the ear analysis further refined the production process, revealing a separate, smaller set of ear molds or application tools, perhaps only 5 or 6 distinct templates, that were used and reused with slight variations across the entire army. This is a critical finding, confirming a strict division of labor. The process suggests that after the head was molded and attached, a different team of specialist artisans, using standardized tools or small molds, would quickly apply the ears, standardizing a feature that is notoriously complex and time-consuming to sculpt uniquely. The analysis of mustaches and beards provides another layer of hidden data. These features were often applied as separate strips or coils of clay. The AI's machine vision algorithms can identify the recurring patterns in the texture and tool marks used to etch the individual hairs onto the clay. By cross-referencing these tool marks with the figure's location in the pit and any accompanying workshop marks, the AI can trace the signature style of individual or small teams of finishers who were responsible for the final aesthetic touches. For example, if a specific pattern of tool marks for the mustache is consistently found on figures whose clay chemistry analysis points to a specific kiln near a certain village, the AI has successfully reconstructed a fragment of the Qin dynasty's labor geography. The AI's ability to reveal these hidden patterns transforms the figures from static art into active data points, providing statistically verifiable answers to questions of logistics and labor management. The overarching theme that emerges is one of modular efficiency. The Army's individuality is a carefully constructed facade, a composite creation built from a limited inventory of interchangeable, mass-produced parts, ensuring a final product that was both uniform in its military professionalism and convincing in its appearance of unique humanity, a perfect reflection of the first emperor's drive for both absolute control and aesthetic grandeur across his entire domain. In the meticulously organized world of the Qin military, even the smallest detail was a coded marker of status and position, and the hairstyles and hierarchy of the terracotta figures provide a stunning, unwritten visual document of this system. For the human eye, the various knots, caps, and hair arrangements are visually fascinating, but for the AI, they are quantifiable data points that allow for the definitive decoding of the soldier's rank by a knot. The hairstyles of the terracotta soldiers are not left to chance. They adhere to a strict, discernible system of military protocol. The most common hairstyle involves a simple top knot placed high and slightly to the side of the head, a style worn by the majority of the unarmored infantry. However, officers, archers, and special units exhibit specific, standardized variations. Archers and charioteers often wear a square cap or a distinctive type of tightly braided bun, perhaps for stability during rapid movement or for ease of helmet wear. The most imposing figures, the high-ranking officers and generals, wear elaborate double-tailed caps or distinctive, winged headgear, a clear and immediate visual symbol of their authority. The challenge for traditional archaeology was the subjective nature of categorization. While an officer's cap is obvious, the subtle differences between the braids of a common infantryman and a specialized crossbow unit required constant visual cross-referencing across thousands of figures. The AI eliminates this subjectivity by transforming the headgear into measurable geometry. By feeding the 3D models of the heads into its system, the AI can perform a geometric classification of the headwear. It can measure precise height of the top knot, the exact angle of the cap's brim, and the number of braids used in the hair coil. This quantitative approach allows the AI to perform a highly accurate ranking correlation analysis. The algorithm correlates the measurable features of the headwear with other known indicators of rank, such as the presence and complexity of the armor and the spatial coordinates of the figure within the battle formation, figures at the rear or center command being higher ranked. The analysis has refined and validated the existing human-derived ranking system, transforming subjective observation into statistically robust proof. For example, the AI has confirmed that figures wearing a specific type of braided bun, previously thought to be simply a regional style, are almost universally found in the first few ranks of the vanguard, confirming their role as specialized, unarmored skirmishers or archers where maximum visibility and speed were paramount. Conversely, the most elaborate, double-knotted caps are consistently correlated with figures possessing the highest degree of detailed, layered armor, confirming their elevated status as field commanders. Furthermore, the AI is capable of identifying anomalies, a figure wearing the hairstyle of a common soldier but found at a critical command position. This anomaly, which might be missed or dismissed by human observers, triggers an alert, prompting archaeologists to re-examine the figure for other subtle clues, such as hidden inscriptions or unique weapon types, potentially indicating a specialized, non-standard assignment within the Qin military hierarchy. The AI's decoding of the soldier's rank by a knot proves that the Qin dynasty military was not only highly structured, but also deeply systematic in its visual communication, using a precise, quantifiable system of uniform and personal presentation to instantly convey the complex chain of command across the vast expanse of the battlefield. The hair of the army, once merely a detail, is now a definitive key to unlocking the organization of the first emperor's eternal military machine. The Terracotta Army's uniforms are a vast, unwritten record of the Qin state's military standards, with the intricate armor patterns holding the key to a wealth of manufacturing secrets and organizational logistics. The armor meticulously sculpted onto the clay figures is not a standardized sheet. It consists of hundreds of individual, overlapping scale plates that vary in size, shape, and lacing pattern depending on the soldier's rank and function. This complex visual data is an ideal subject for AI analysis, transforming the aesthetic detail into a definitive data source. The soldiers are broadly classified into unarmored, archers, skirmishers, lightly armored, standard infantry, and heavily armored officers, charioteers. The difference lies in the complexity and coverage of the scale armor. Officers wear chest plates, shoulder guards, and even armored skirts, while common infantry may only have a simple plate over their torso. The crucial hidden data lies in the geometry of the scales themselves. Each scale is a tiny, overlapping rectangle or square, sometimes rendered with small rivets or tie holes. To the human eye, the thousands of scales blur into a complex texture. But to the AI, each scale is a unique, measurable entity. The AI's machine vision algorithms are used to perform a scale geometric analysis, measuring the precise dimensions, overlap ratio, and lacing whole pattern of thousands of scales across various figures. The results have been revolutionary in proving the extent of Qin dynasty standardization. The AI has confirmed that specific scale patterns, the combination of scale size and lacing detail, are consistently correlated with specific ranks, moving the identification of rank from inference to geometric proof. Furthermore, the AI can distinguish between different tooling techniques used to score the lines representing the scales and the individual rivets. This surface analysis can reveal the subtle differences between various artisan groups. For example, one team may have used a specialized 5-prong rake tool to score the scale lines, while another used a simple single-point stylus. The AI can classify and trace these specific tool marks across the entire army, creating a definitive map of the production workflow and identifying specific manufacturing workshops. This is crucial for understanding the logistical supply chain. If a specific armor pattern created with a certain tool mark is predominantly found on figures made of clay from a particular geological source, the AI has successfully reconstructed a portion of the Qin industrial logistics. Workshop X, utilizing clay source Y, produced armor pattern Z. This level of integration provides an unprecedented, holistic view of the first emperor's industrial capacity. The AI analysis also sheds light on the mass production secrets of the empire. The scale of the armor construction suggests the use of standardized templates for entire sections of the armor, a rigid, early form of industrial design that ensured uniformity across thousands of figures produced over decades. By tracing the recurrence of specific geometric armor sections, the AI is revealing the Qin dynasty's methods for maintaining quality control and achieving rapid output, proving that the ancient empire utilized sophisticated, modern concepts of standardization and modularity that have remained an unwritten record until the arrival of the machine. The armor, once seen as a decorative shell, is now the definitive, quantifiable industrial logbook of the Qin state. The vast scale of the Terracotta Army project, consuming the labor of hundreds of thousands of conscripts and artisans over 40 years, necessitated a distributed, highly organized industrial structure. The process of identifying individual artisan workshops, the forensic forge, is a key objective of the AI analysis, aiming to map the organizational logistics of this massive ancient production line. Traditional methods relied primarily on the faint inscriptions and markers left on the figures by the artisans or supervisors, simple characters indicating a name or a location. However, many figures lack these inscriptions, or the marks are too faint or ambiguous to reliably link to a workshop. The AI, therefore, approaches this challenge using a multi-layered forensic investigation that combines material science with geometric analysis. The first layer is clay chemistry and elemental analysis. Samples of clay from the figure's torsos, heads, and limbs are analyzed using methods like X-ray fluorescence, XRF, or neutron activation analysis, NA. The elemental composition of the clay, the trace amount of elements like aluminum, silicon, iron, and potassium, provides a unique geological fingerprint that can be traced back to the specific pit or riverbed where the clay was originally sourced. By feeding this chemical data into the AI, the algorithm can cluster figures based on the statistical similarity of their clay composition, effectively mapping the figures to their geographical origin before they ever reach the kiln. The second, more subtle layer is tool mark and geometric signature analysis. As demonstrated in earlier chapters, the AI can isolate the geometry of individual features like ears, armor scales, and hair textures. By performing a surface roughness and tool mark analysis, the AI can identify consistent, reproducible patterns in the way the clay was finished. These patterns are essentially the signature style of a specific artisan or a small team working with the same set of tools. The AI can statistically link a specific finishing style, e.g., a specific way of braiding the hair or applying the armor rivets, to a group of figures. The final, crucial layer is the data fusion and correlation. The AI cross-references the three datasets: the geological clay fingerprint, what materials came from, the tool mark signature, who finished the product, and inscribed markers to confirm names of workshops. For instance, the AI might find that all figures containing clay from the Yellow River Pit geology and exhibiting the 6-point rake finish tool mark also contain the inscribed marker gong, artisan name. This powerful, statistically verified correlation allows researchers to definitively reconstruct the operating procedure of the gong workshop, mapping its supply chain and its unique production style across the entire army. This process has transformed the study of the Terracotta Army from a single, unified artifact into a distributed network of decentralized production units, revealing the stunning administrative capacity of the Qin Empire to manage and coordinate a massive industrial effort. The forensic forge has demonstrated that the figures were not created in one central facility, but by multiple, highly organized workshops, confirming the first emperor's reliance on efficient, standardized logistics to build his eternal guard. The production of the Terracotta army, consuming 40 years of labor and resulting in thousands of life-size, yet seemingly unique figures, presents an ancient assembly line mystery. The evidence suggests a logistical genius rooted in the principle of standardized parts and mass production, concepts modern industry takes for granted but which were revolutionary and unprecedented in the ancient world. The question is not how they produced the figures, but how they achieved such efficiency while maintaining the illusion of individuality. The answer, verified by the AI's rigorous geometric analysis, lies in modular construction. The terracotta soldiers were not sculpted as single, monolithic pieces of clay. Instead, they were constructed using a series of separate, standardized components created using molds and templates, a method that allowed for rapid high-volume output. The AI has confirmed that the body itself was constructed in stages, a solid base of the legs, a hollow cylinder for the torso, and separate, specialized molds for the arms, hands, and the various headgear. This system of standardized parts offered two immense advantages to the Qin state. First, it allowed for decentralized, parallel production. Different workshops could specialize in different components. One kiln complex focusing solely on legs, another on torsos, before the parts were transported to a central assembly area for final construction and customization. This modular approach drastically reduced the overall production time, a crucial necessity for the first emperor's 40-year deadline. The AI's analysis of the limb geometry supports this finding. By measuring the length and angle of thousands of arms and legs, the algorithms confirm that while there are minor variations for opposing purposes, the underlying dimensional characteristics fall into a small number of distinct, standardized templates. Second, the standardized parts allowed for interchangeability and easy repair. The ability to use a common mold for a torso meant that damage during transport or firing could be quickly rectified with a replacement part from the same production line. This efficiency was paramount for managing a project of this scale. The most fascinating aspect, however, is the final customization applied to these standardized parts. The AI-verified existence of a limited number of base head molds proves that the illusion of uniqueness was layered onto a foundation of standardization. The individual sculpting of the ears, the unique tooling of the armor scales, and the application of individualized facial features were all fast-applied aesthetic layers designed to cover the mass-produced core. This is the assembly line mystery solved. The Qin dynasty achieved both speed and individuality by treating the soldier not as a singular work of art, but as a composite structure built from a foundation of standardized, interchangeable parts. The AI, by mathematically segmenting and analyzing the various components, from the core torso geometry to the final mustache texture, has successfully reverse-engineered the first emperor's ancient production line. The results demonstrate a level of industrial organization, standardization, and quality control that pushes the boundaries of what was previously believed possible for an ancient, pre-industrial civilization, confirming the terracotta figures as one of history's earliest and most compelling examples of sophisticated mass production techniques. Scattered across the terracotta figures and the weapons they once carried are faint, often overlooked indicators of their origin and quality, the hidden code contained within inscriptions and maker's marks. These simple, incised characters are physical evidence of the Qin dynasty's renowned system of accountability, an imperial mandate that required artisans and supervisors to leave their names on their work. While visible to the human eye, the true complexity and breadth of this system could only be revealed to the AI's rigorous analysis and correlation. The inscriptions found on the figures themselves are often located on inconspicuous areas, such as beneath the robes near the base of the torso or inside the hollow heads. These marks typically consist of a single character or a combination of characters, naming the individual artisan, the workshop supervisor, or the governmental department responsible for the figure's production. Inscriptions on the bronze weapons are even more common and detailed, often listing the manufacturer, the quality inspector, and the year of manufacture, confirming the astonishing level of quality control exercised by the Qin government. Traditional archaeology struggled to analyze the inscriptions comprehensively because of the sheer volume of data, the varying quality of the incisions, and the fragmentation of the figures. The AI overcomes these challenges through two methods. First, it uses high-resolution imaging and character recognition software to create a comprehensive, clean database of every single mark found. Second, and most critically, the AI performs a sophisticated cross-correlation and spatial analysis to link these marks to the figure's physical characteristics. The hidden code is cracked when the AI links the inscribed mark to the geometric and chemical signatures. For example, the AI can correlate a figure bearing the inscribed name Chao with figures that share the same tool mark signature on their armor scales and the same clay chemical composition. This correlation mathematically verifies that the artisan Chao worked in a specific workshop using a specific type of clay and was responsible for a specific style of finishing. This process allows researchers to move beyond simply reading the names to fully reconstructing the organizational chart of the Qin production line, detailing the geographical distribution of labor and the specialization of each team. Furthermore, the analysis of the inscribed quality marks on the bronze weapons, which were found alongside the terracotta figures, reveals the astonishing level of accountability within the Qin military-industrial complex. The marks confirm a system that traced every weapon, from the raw bronze ingot to the final, polished crossbow trigger mechanism, back to the individual inspector responsible for its quality. This strict system, enforced under the threat of severe punishment for any defects, explains the extraordinary standardization and quality of the Qin bronze arsenal. The AI's ability to analyze and correlate this hidden code confirms that the Terracotta Army is not just an archaeological treasure, but a powerful, unwritten logbook of ancient China's administrative, industrial, and military accountability. A system whose efficiency was unparalleled in the ancient world. The marks confirm that the first emperor's control extended not just to the battlefield, but to the very foundation of the manufacturing process. The Terracotta Army's arrangement in the excavation pits is a three-dimensional manifestation of the geometry of war, a physical blueprint of Qin dynasty military doctrine. While archaeologists established the basic formation, the vanguard, the main body, the flanks, the subtle, systemic rules governing the precise positioning of the thousands of figures remained obscured by the scale. AI modeling of the pit's tactical formation is now revealing the hidden mathematical logic that dictated the battlefield placement of the first emperor's eternal guard. The analysis begins by converting the entire excavated area, Pit 1, Pit 2, and Pit 3, into a massive georeferenced spatial dataset. Every figure is defined not only by its 3D geometry, but by precise XYZ coordinates within the pit. The AI is then deployed to perform statistical spatial analysis to search for non-random patterns in the distribution of different figure types. The key question is whether there are mathematically significant correlations between a figure's characteristics, rank, armor type, weapon, and its position relative to other figures and the pit's boundaries. The AI's findings have provided revolutionary insights into unit organization and command structure. For example, the algorithm confirms with statistical certainty that figures identified as high-ranking officers, based on headgear and armor complexity, are consistently positioned at the precise geometric center of a cluster of unarmored and lightly armored infantry, and often exactly one chariot link behind the vanguard. This mathematically verifies the Qin military's reliance on centralized field command and provides the exact organizational template for a standard unit. Furthermore, the AI models are revealing the subtle tactical logic of the formation. By modeling the lines of sight and inter-unit spacing between the figures, the algorithm confirms that the arrangement was not merely symbolic, but highly functional. The spacing between the columns is optimized for rapid defensive maneuvering, and the precise angle of the figure's feet and bodies suggests a subtle but unified direction of movement and engagement. This spatial analysis allows researchers to virtually simulate the Qin battle formation, transforming the static army into a dynamic, analyzable model of ancient battlefield strategy. The AI's work has also been instrumental in identifying the precise placement of specialized units. The analysis of the archer and crossbow units in the vanguard confirms a mathematically optimized configuration designed for a devastating layered projectile attack. The front row standing archers are spaced to allow maximum rate of fire, while the rear row kneeling archers are positioned to fire over the heads of the front rank, a classic, disciplined volley fire formation that maximizes lethal density. The geometry of war, once a silent mystery, is now being spoken in the clear language of coordinates and statistical modeling. The AI is successfully reverse engineering the Qin dynasty's battlefield doctrine, proving that the army was not just a symbol of power, but a meticulously planned and geometrically perfect instrument of imperial military might, whose final, precise placement was determined by a rigorous, calculated logic. The final, essential stage of the AI-driven study of the Terracotta army is the digital resurrection, the monumental effort to rebuild the army piece by piece not in clay, but in code. The vast majority of the excavated figures were shattered by the collapse of the timber roof, leaving behind millions of fragments and shards that require painstaking manual reconstruction. This manual process is incredibly slow, often taking weeks or months to reassemble a single soldier. The digital approach, however, offers a revolutionary solution, utilizing sophisticated algorithms to perform the ultimate three-dimensional jigsaw puzzle. The process begins with a fragment library. Every shard of terracotta recovered is individually scanned using high-resolution 3D scanners, creating a comprehensive database of digital fragments, millions of unique geometric shapes defined by their specific coordinate data. The challenge is immense because the fragments lack clear visual cues, and the breaks are often complex, nonlinear fractures. The AI is deployed to solve this problem using geometric matching algorithms. The core of the algorithm is a function that compares the edge geometry of two fragments, calculating the statistical probability that their broken surfaces, their fracture interfaces, were once contiguous. The algorithm analyzes the minute irregularities, the ridges, and the valleys of the broken edge, treating the fracture as a unique, complex fingerprint. By comparing millions of pairs of fragments, the AI rapidly identifies high-probability matches, performing a task that would take a human thousands of years to complete manually. The success of this digital resurrection is not just speed, it is accuracy. The geometric matching, based on precise 3D data, offers a level of verification that surpasses manual reconstruction. When the AI identifies a match with a 99% geometric confidence score, the two fragments are digitally snapped together, forming a partial figure. The AI then continues this iterative process, building out the figure from dozens or even hundreds of fragments, creating a complete digital model of figure that may still be in pieces in conservation lab. The resulting digital twin provides immediate, invaluable information to the human conservators. It shows them precisely which fragments belong together and the exact angle and position required for physical reassembly, dramatically reducing the time and risk of error in the manual reconstruction process. Furthermore, the AI can perform predictive reconstruction. By analyzing geometry of a figure's surviving components, torso, upper legs, and comparing it to completed models in its library, the AI can predict the likely size, shape, and even the armor type of the missing fragments, guiding future excavation and reconstruction efforts. The digital resurrection transforms a fragmented past into a complete, analyzable future. It ensures that the millions of broken pieces are not just cataloged, but are actively contributing to the overall understanding of the Army's organization, allowing researchers to study the complete anatomy of figures that may never be fully reassembled in the physical world. The AI is effectively serving as the ultimate conservator, meticulously piecing together the silent, shattered guard of the first emperor. When the Terracotta army was interred, it was not merely an army of clay. It was an army equipped with intricate elements made of organic materials that have long since perished, creating a historical void, the unseen material. The soldiers' crossbows, the shaft of their halberds and spears, the carriages and wheels of their war chariots, and the protective lacquer and paint that gave them their dazzling colors were all made of wood, bamboo, cloth, and leather. Over 2 millennia of subterranean dampness, these organic components disintegrated, leaving only soil stains, faint impressions, and the astonishingly preserved bronze weapon components. Reconstructing this lost material world is a critical objective of the AI analysis, aiming to bridge the gap between surviving inorganic clay and a complete, functional military unit. The key to this reconstruction lies in the digital analysis of negative space. As the organic materials, specifically the massive wooden structures of the chariots and the long, thin wooden shafts of the weapons, decayed, they left behind clear, identifiable soil impressions within the pits. Archaeologists painstakingly record these impressions through plaster casting and high-resolution photography. The AI is then deployed to analyze this evidence using computational geometry. By modeling the negative space defined by the soil impressions, the algorithm can reverse engineer the original object's dimensions, volume, and structure. For example, by analyzing the 4 perfectly spaced rectangular impressions that once held the wheels and axle of a war chariot, the AI can precisely model the chariot's original wheelbase, ground clearance, and the diameter of its wooden wheels, providing vital engineering data that complements the surviving bronze fittings. Crucially, the AI is essential for reconstructing the lacquer and paint layers. As noted previously, the vibrant colors faded rapidly upon excavation, but the underlying lacquer, often applied in multiple thin layers, left behind microscopic organic residues and chemical traces. The AI, processing data from multispectral imaging and chemical residue analysis, is identifying the pattern and thickness of these lacquer layers. This allows researchers to not only digitally restore the colors, but also to understand the material science of Qin dynasty preservation techniques. The lacquer was essential for providing a smooth, durable surface for the pigments, demonstrating an advanced understanding of organic chemistry and material preparation. The most dramatic application of this reconstruction is the arsenal of crossbows. While the highly complex bronze trigger mechanisms are perfectly preserved, the wooden stock, tiller, and bow stave have vanished. By analyzing the faint soil stain where the wooden components lay, the AI can model the size, shape, and draw weight capacity of the original crossbows. By combining this information with the AI-verified data on the bronze trigger standardization, which confirm the high degree of interchangeability, the AI can definitively prove that the Qin military possessed a massive, standardized, and highly sophisticated ranged weapon system, a finding that profoundly alters our understanding of ancient Chinese military technology. The reconstruction of the unseen material is therefore far more than an artistic exercise. It is a vital step in transforming the static terracotta figures into a complete functional and historically accurate model of the first emperor's fully equipped, combat-ready army. The void left by 2,000 years of decay is now being filled by the precise, quantifiable logic of machine, completing the picture of the Qin state's unprecedented industrial and military genius. The bronze weapons recovered from the terracotta army pits are not merely artifacts. They are a profound, tangible testament to the Qin dynasty's industrial and administrative genius, epitomized by the crossbow complex. The recovery of thousands of bronze arrowheads, spear tips, swords, and most tellingly, the highly intricate, multi-component bronze crossbow triggers provided archaeologists with an unprecedented look into ancient metallurgy and military production. The AI's analysis of this arsenal confirms a revolutionary historical fact. The Qin Empire was the first major civilization in world history to implement total standardization and interchangeability in its mass-produced military weaponry. The focus of the AI analysis fell heavily on the crossbow triggers. These triggers are complex mechanisms consisting of up to 7 individual bronze components that must fit together with extraordinary precision for the weapon to function reliably. In the ancient world, it was standard practice to handcraft and file each weapon part, meaning a replacement part from a different weapon would rarely fit. However, the AI-driven medical analysis of thousands of recovered triggers, measuring the components to within a fraction of a millimeter, revealed a stunning truth. The parts were so geometrically identical that they were perfectly interchangeable. A lever from one crossbow could be seamlessly swapped into the housing of another, a revolutionary concept of mass production centuries ahead of its time. To achieve this, the Qin state utilized a system of highly standardized molds and templates, coupled with a rigorous quality control and accountability system. The AI modeled the manufacturing process, confirming that the parts were produced in batches using a limited number of master molds, ensuring uniformity. Furthermore, the AI performed a spatial and chemical correlation between the crossbow triggers and their placement in the pits. The algorithms found that triggers with subtle differences in their trace metal composition, a chemical signature indicating a specific batch or workshop, were often clustered in specific, defined areas of Pit 1. This suggests a cellular production model, where small teams of artisans were responsible for producing a batch of triggers, and that these batches were then delivered directly to specific areas of the pit for final assembly and armament of the terracotta figures. This correlation is a physical blueprint of the Qin logistical chain, tracing the journey of a weapon from its forensic forge to its final, strategic placement in the formation. The standardizing of ancient weaponry through the crossbow complex proves that Qin Shi Huangdi's administrative control extended deep into the empire's industrial heartland, enforcing strict quality control and dimensional uniformity across a highly distributed manufacturing network. This level of standardization meant a tactical advantage for the Qin military: faster field repairs, simpler training, and the ability to maintain a massive, highly effective, projectile-based army. The crossbows are no longer merely ancient weapons. They are the ultimate quantifiable evidence of the first emperor genius for imperial-scale industrial logistics, a truth that could only be extracted by a machine capable of measuring and correlating the geometry of thousands of bronze artifacts across a massive subterranean battlefield. The terracotta army figures exhibit an immediate, striking realism, but their construction adheres to a subtle, hidden logic rooted in the geometry of height. The figures vary in stature, a phenomenon not random but directly correlated with their military rank, creating a visual, standardized hierarchy. The AI analysis of this dimensional data reveals the Qin artisans' methods for standardization of the human form and how they use height as a key metric for defining military status. The figures generally range from approximately $1.75 meters, about 5 feet 9 inches, to just over $2.0 meters, about 6 feet 7 inches. The most obvious finding, confirmed and quantified by the AI, is a clear relationship between height and rank. The tallest figures are consistently the generals and high-ranking officers, while the shortest figures are generally the unarmored infantry and archers. This is not simply an artistic choice, but a deliberate, systematic enforcement of military protocol, using physical height as a proxy for authority and status, a tradition common in many martial cultures. The AI's contribution is to move beyond this visual observation to quantify the dimensional standardization within each rank. By processing the 3D point cloud data of thousands of figures, the algorithm can calculate the precise height, shoulder width, and limb proportions for every single soldier. The AI's clustering analysis reveals that the figures do not adhere to a perfect, continuous distribution of height. Instead, they group tightly around specific, distinct height averages, suggesting the use of standardized dimensional templates for each rank. For example, the majority of foot soldiers might cluster around an average of $1.78 meters, while junior officers might cluster around $1.85 meters, and generals around $1.98 meters. These clusters indicate that the artisans were likely instructed to adhere to specific, predetermined height-based molds or construction specifications for each rank type. This finding is crucial because it confirms that the Qin military enforced a clear, measurable visual hierarchy. The height of the figure was not merely symbolic. It was an integral part of their uniform and insignia. An officer's increased stature would have been instantly recognizable and commanding on the actual battlefield, and the terracotta version perfectly replicates this imperative. Furthermore, the AI's analysis extends to proportionality within the height clusters. By comparing the limb lengths and torso volumes across the standardized height groups, the algorithm can determine the efficiency of the modular construction. It confirms that the taller figures were created not just by scaling up the entire model, but by using longer leg molds or taller cylindrical torso components, effectively maintaining a system of interchangeable parts across different stature requirements. The geometry of height thus proves that the Qin artisans were masters of variable standardization, capable of efficiently mass-producing figures of differing sizes, while maintaining overall proportional consistency and adhering to a strict, rank-based dimensional code. The final, fascinating implication is that the figures may reflect the actual recruitment standards of the Qin army, suggesting that the generals in the living world were indeed selected partly based on their imposing stature. The AI has transformed the simple measurement of height into a definitive key for decoding the strict, organized hierarchy of the first emperor's army. The Terracotta army is not solely composed of infantry. Its ranks include a crucial component of ancient warfare, the chariot corps, whose complex construction provides a high-level challenge for reversing the engineering of bronze and wood. The war chariots, once the supreme expression of military technology and noble status, have largely disintegrated, leaving only the remnants of their bronze fittings, weapon inventory, and the faint soil impressions of the massive wooden structure. Reconstructing these vital military vehicles requires a sophisticated convergence of AI modeling, metal analysis, and computational geometry. The original Qin war chariot was a highly engineered, light, and durable fighting platform pulled by 4 horses. The core challenge is that the most massive components, the wheels, axles, carriage bed, and protective shield, were made of wood and have vanished. The surviving evidence consists of the numerous bronze components, the axle caps, linchpins, decorative fittings, and, most importantly, the complex yoke and harness attachments. The AI's initial task is to create a complete, high-resolution 3D model of every surviving bronze component from a chariot pits. The algorithm then performs a component fitting analysis. It uses the precise geometry of the bronze fittings, the sockets, slots, and bolt holes to mathematically determine the required dimensions and shape of the wooden components they once attached to. For example, the size and curvature of the bronze axle caps precisely define the diameter of the wooden axle, while the shape of the yoke fasteners dictates the size and angle of the wooden yoke beams. This process of reverse engineering the wood from the bronze allows the AI to virtually rebuild the entire skeletal structure of the Qin war chariot with engineering accuracy. Furthermore, the AI is modeling the structural dynamics and stability of the reconstructed chariots. By inputting the estimated weight of the completed structure, wood, 2 armored drivers/fighters and 4 horses, and the estimated terrain conditions of the ancient battlefield, the algorithm can simulate the chariot's center of gravity, load-bearing capacity, and turning radius. This simulation is critical for understanding the tactical role of the chariot corps, confirming its speed and maneuverability on the battlefield. The analysis also sheds light on the logistics of construction. By analyzing the standardized size and material signature of the bronze fittings, the AI confirms that the chariot components, much like the crossbow triggers, were produced using standardized molds across a distributed production network. This high level of standardization was essential for rapidly assembling and repairing the chariots in the field, making the chariot corps a flexible and sustainable element of the Qin military. The reversing the engineering of bronze and wood has transformed the faint impressions in the earth into a comprehensive, working model of Qin dynasty military vehicle technology. The resulting digital twin of the war chariot is not a guess. It is a mathematically and structurally verified reconstruction of a highly sophisticated piece of ancient engineering, revealing the full extent of the first emperor's technological and logistical prowess in deploying a fully motorized, standardized fighting force. Within the vast, complex dataset of the Terracotta army, the AI is not just finding patterns. It is finding the absence of expected patterns, revealing a subtle, elusive entity that researchers have dubbed the plywood phantom. This phantom represents the statistical signature of the unknown, the presence of an unseen or unexcavated element that is required to make the existing, known data complete and logically consistent. The concept of the plywood phantom arises from the AI's predictive modeling of the formation's composition. As the algorithms analyze the ranks and distribution of the figures in the excavated pits, Pit 1, Pit 2, Pit 3, they confirm a highly structured, statistically predictable organization based on the known Qin military hierarchy. However, The AI notes that for the system to be a truly complete, functional reflection of the Imperial Army, there should be a corresponding presence of figures representing non-combatant roles, logistical support, medical personnel, intelligence officers, or dedicated engineering units. These roles, while essential for a massive army, are largely absent from the excavated figures, which focus heavily on frontline combatants. The statistical signature of this absence, the functional necessity of these roles within the model versus their physical absence in the pits, is the plywood phantom. The AI is now tasked with actively searching for the physical evidence of this phantom through spatial anomaly detection outside the main formations. By processing the high-resolution magnetometry data and cross-referencing it with the required logistical unit structure derived from the military models, the AI is prioritizing specific, unexcavated areas near the periphery of the pits. These high-priority anomalies are locations that could house small, dedicated pits containing these unrepresented logistical or administrative units. For example, the AI might identify an anomaly that is too small for a full combat formation, but perfectly sized for a pit containing figures of scribes or quartermasters who would have been essential for managing the standardized weapons inventory and troop movements. This search is guided by the fundamental logistical logic confirmed by the AI. The first Emperor's vision was one of functional completeness. A functional shadow army cannot exist without support, and the statistical model confirms that the support staff, the plywood phantom, must exist somewhere within the 60 square kilometer complex. Furthermore, the concept extends the production process. The AI models the immense consumption of wood, fabric, and rope required for the army and predicts the existence of dedicated supply and storage pits near the main construction zones. An anomaly that matches the statistical size and composition of a massive, long-term timber storage facility, based on the logistical flow models, is another manifestation of the plywood phantom. The plywood phantom is a powerful illustration of AI's generative power in archaeology. It uses the quantifiable known to hypothesize the unquantifiable unknown, transforming the absence of evidence into the evidence of absence. The search for this statistical signature is driving the next phase of non-invasive exploration, aiming to complete the organizational chart of the Eternal Guard and finally account for the logistical support that sustained the First Emperor's colossal military ambition. The leadership structure of the Eternal Guard, the officer corps, is instantly discernible to the naked eye, but the AI analysis is now decoding authority in the subtle details, uncovering precise, quantifiable rules that govern the uniform, armor, and posture of the high-ranking figures. The officers are the key to understanding the full command structure of the Qin military, and their figures are among the most individualized and meticulously crafted. Officers are easily identified by their height, their complex headgear, and their layered, detailed armor. The AI's contribution is to move beyond these general visual markers to establish a definitive algorithmic ranking system. The algorithm uses feature vector analysis to assign a numerical value to every relevant feature: the geometric complexity of the armor plates, the height of the ceremonial knot or cap, the number of braids in the hair, and the degree of ornamentation on the chest. By aggregating these values across all officer figures, the AI can perform a hierarchical clustering analysis, mathematically sorting the officers into distinct, statistically verifiable ranks, from the lowest field commander to the supreme general. The analysis of the armor complexity is particularly revealing. While infantry armor is functional and standardized, officer armor is often highly ornamental, with intricate lacing, specialized shoulder guards, and decorative fasteners. The AI's geometric analysis measures the number of scales, the overlap ratio, and the precision of the surface tooling, confirming that the level of armor detail is a direct, linear function of rank. The most senior officers with the most geometrically complex and meticulously rendered armor, an investment of artisan labor that reflects their elevated status. Furthermore, the AI is decoding authority through posture and gesture. Officers are often sculpted in distinct, commanding poses. One hand may rest on the hilt of the sword, while the other is held in a gesture of command or contemplation. By using skeletal frame modeling on the 3D scans, the AI quantifies the precise angle of the officer's head, the stance of the feet, and the extension of the arms. It confirms that these postures are not random but adhere to a small, standardized library of command poses, each likely encoding a specific military function or a level of authority. For instance, the posture or general position at the rear of Pit 1 is statistically distinct from the posture of a cavalry commander in Pit 2, suggesting a visual vocabulary for different types of command roles. The most compelling discovery is the detection of subtle anomalies that denote exceptional status. The AI is trained to flag officers whose feature vectors do not align perfectly with the established clusters, an officer with the armor complexity of a junior commander, but the headgear of a high-ranking general, for example. These anomalies prompt human researchers to investigate the figure for unique inscriptions or non-standard weaponry, potentially identifying specialized, non-hierarchical roles such as Inspector General or Imperial Envoy, positions of authority that transcended the standard military chain of command. The AI's decoding of the officer corps confirms that the Qin military was a highly formalized and strictly hierarchical institution, where authority was not just granted but was visibly and quantifiably engineered into the very clay of the figures, with every subtle detail serving as a precise marker of command and control. While Pit 1 holds the main battle formation, Pit 2 is home to the specialized forces, dominated by the cavalry contingent, whose arrangement and unique equipment are now being analyzed by AI to unlock the secrets of Pit 2. This chamber, shaped like an irregular L, provides a fascinating glimpse into the elite, rapid response units of the Qin military, units essential for skirmishing, reconnaissance, and rapid flank maneuvers. Pit 2 contains a complex mix of figures, kneeling archers, war chariots, and most prominently, over 100 figures of cavalrymen accompanied by their life-size terracotta horses. The cavalry figures are distinct from the main infantry. They wear shorter robes, protective headwear, a pillbox hat or cap, and lighter armor, signify their need for speed and mobility. The AI's initial task focused on the geometric analysis of the horses. These figures are incredibly realistic and anatomically correct, a feat of artistry and engineering. By analyzing the 3D models of the horses, the AI confirms that they were constructed using highly standardized body molds, but with subtle, individually sculpted muscle definition and facial features. The most crucial finding is the analysis of the harness and tack. The terracotta cavalrymen were sculpted holding the reins, which have long since perished, but the AI, by modeling the position of the hands and the pressure points on the horses' necks, can accurately reconstruct the original configuration of the reins and bits. This detailed reconstruction reveals the exact riding style of the Qin cavalry, whether they rode using a simple rope bridle or a more complex leather harness, providing invaluable data on ancient equestrianism and tack engineering. Furthermore, the AI is unlocking the secrets of the unit organization within Pit 2. The arrangement is clearly sectioned, a central area for chariots, a vanguard of kneeling archers, and the main body of cavalry. The AI is performing a spatial correlation between the cavalrymen and the kneeling archers. The analysis confirms a predictable ratio and specific inter-unit spacing between the two groups, suggesting that the cavalry and archers were intended to operate as an integrated, combined arms unit, with the cavalry providing rapid mobility and the archers providing concentrated projectile fire, a classic strategy for overwhelming an enemy flank. The AI's work is also providing new data on the cavalry's weaponry. The cavalrymen typically carried long lances or spears, whose wooden shafts have vanished. By analyzing the grip of the cavalrymen's hands and the length of the soil impressions, the AI can precisely model the optimal length and weight of the original weapons, confirming their role as mobile shock troops. The unlocking of Pit 2 through AI analysis has transformed our understanding of the Qin military's complexity, revealing that the army was not monolithic, but composed of highly specialized, integrated units. The cavalry contingent, with its standardized horses, light equipment, and precise formation, stands as proof of the first emperor's commitment to building a well-rounded, tactically superior eternal army capable of utilizing the full spectrum of ancient warfare strategies. The most formidable aspect of the Qin military was its overwhelming projectile firepower, embodied by the massive ranks of archers and crossbowmen whose figures are scattered throughout the pits, particularly the vanguard of Pit 1 and the specialized unit in Pit 2. The AI is now focusing on the archer's stance, utilizing biomechanical and geometric modeling to understand the sheer scale and efficiency of the Qin state's range combat capacity. The figures provide two distinct archetypes for analysis: the standing archer unarmored, positioned at the front of the ranks, and the kneeling archer armored, positioned behind the standing archers or in specialized reserve units. The kneeling archer, in particular, is captured in a famous, highly dynamic pose, a figure resting one knee on the ground while holding the crossbow or bow taut, ready to fire. The AI's first task is biomechanical reconstruction. By analyzing the 3D models of the archer's bodies, specifically the angle of the limbs, the tension in the sculpted muscles, and the position of the hands, the algorithm can accurately model the maximum potential draw weight of the crossbows and bows they once held. This analysis, combined with the AI-verified standardized dimensions of the crossbow triggers, provides a definitive, quantifiable estimate of the crossbow's penetration power and range. The data confirms that the Qin military possess weapons capable of delivering lethal force over long distances, a tactical game-changer in ancient warfare. Furthermore, the AI models the tactical advantage of the stance. The difference between the standing archer and the kneeling archer is more than aesthetic. It is a tactical instruction. The kneeling stance offers stability and a lower profile, ideal for maintaining accuracy and reducing vulnerability under prolonged, layered fire. The AI spatial analysis confirms that the kneeling archers were placed to fire over the heads of the standing archers in the front ranks, ensuring a continuous, sustained barrage. The algorithm models a perfect inter-unit spacing and height difference required for this volley fire strategy to be maximally effective without friendly fire casualties, a clear indication of disciplined, high-level tactical planning. The most complex AI task is the modeling of projectile efficiency. By integrating the known number of archer figures in the pits, the estimated rate of fire for a Qin crossbow, and the AI-calculated standardized arrow inventory, the algorithm can simulate the total volume of fire the Eternal Guard was designed to unleash. The sheer scale of this model firepower is overwhelming, confirming that the Qin military relied on coordinated, mass projectile attacks to rapidly break enemy formations before the infantry closed for combat. The AI's analysis of the archer's stance and the standardization of their weaponry confirms that the Terracotta army is not just a defensive guard, but a highly effective, offensive fighting force designed to dominate the battlefield through a technologically superior and perfectly modeled projectile fire dominance. This dominance was a tactical secret that enabled Qin Shi Huangdi to unify the warring states and conquer all opposition. The creation of the Terracotta army required an immense, sustained supply of raw material, the earth itself, making clay chemistry a vital data source for tracing the supply chain of the earth. The figures were constructed from local lush clay, a fine, wind-blown silk common in the Xi'an region. However, the exact source and consistency of this clay varied, and these subtle, mineral differences act as an irreversible geological fingerprint that can be decoded by AI and material science. The methodology involves non-destructive elemental analysis, primarily using techniques like X-ray fluorescence (XRF) and neutron activation analysis (NAA) to determine precise chemical makeup of the terracotta samples. These techniques measure the unique proportions of trace elements like potassium, titanium, iron, and various rare earth metals within the clay structure. The specific combination of these trace elements is directly linked to the geological profile of the clay's origin pit or riverbed. By collecting thousands of samples from various body parts, torsos, heads, limbs, and feeding the resulting elemental profiles into the AI, the algorithm performs a chemical clustering analysis. The AI can identify groups of figures that share a statistically identical chemical signature, indicating that they were manufactured using clays sourced from the same geological location, even if they were found in widely separated areas of the mausoleum complex. This chemical clustering provides definitive proof of the decentralized, distributed nature of the production. The AI's analysis has confirmed the existence of at least several distinct clay sources used throughout the 40-year construction period. Crucially, The AI performs a three-way correlation between the clay chemistry, the geometric tool marks, and the figure's final placement in the pits. For instance, the algorithm might find that figures made of clay source A are consistently finished with tool mark set X, identifying a specific workshop, and are always deployed in the northern flank of Pit 1. This correlation reconstructs a segment of the chain logistical chain. A specific clay source fed a specific, identifiable workshop, and that workshop's output was systematically assigned to a specific military unit and geographical position in the Eternal Guard. This high-level, integrated analysis reveals the extraordinary administrative control of the imperial state over its raw materials and labor. The government not only dictated the style and rank of the figures, but also controlled the entire upstream supply process, ensuring that the clay sourced from various parts of the region was systematically channeled to the correct workshops. The clay chemistry is thus transformed from a simple material property into a quantifiable logbook of ancient industrial organization. The tracing of the supply chain of the Earth proves that the first emperor's command over his empire extended to the very geological foundation of his final, eternal project, a massive, orchestrated effort whose efficiency was preserved in the mineral structure of the clay itself. The long-term survival of the fragile Terracotta army, now facing the dual threats of natural decay and irreversible damage from exposure, relies fundamentally on the role of the digital conservator, the integration of AI for preservation and restoration. The machine is not merely a tool for historical discovery. It is a critical instrument for the long-term, non-destructive stewardship of this irreplaceable cultural heritage. The most immediate application is predictive decay modeling. The high-resolution 3D point cloud models serve as the perfect baseline for monitoring the Army's condition. The AI is fed continuous data from environmental sensors in the pits, temperature, humidity, and airflow, and is trained to analyze new, periodic 3D scans. By comparing a new scan to the initial, perfect digital twin, the algorithm can detect and quantify minute submillimeter changes in the figure's surface geometry, such as the growth of salt crystals, the formation of new cracks, or the subtle shifting of fragments. The AI can then use this data to predict the rate and location of future decay, creating a highly accurate risk map for conservators. This predictive capability allows conservation efforts to be proactive, intervening precisely where and when the risk is highest, rather than waiting for visible damage to occur. A second crucial role is automated reconstruction assistance. The AI's capacity for geometric matching is continuously used to aid the manual reassembly of the thousands of shattered figures. The algorithms rapidly identify high-probability matches between fragments and provide the human conservators with precise digital blueprint for reassembly. This reduces the time a fragile fragment is exposed or handled, thereby minimizing the risk of further physical damage. The AI essentially becomes a digital planning phase for the physical manual work, turning a years-long manual jigsaw puzzle into a computationally guided assembly process. Furthermore, the AI acts as a digital restorer for the lost color. While the original pigment are almost entirely gone, the AI's analysis of the residual chemical traces and lacquer structure allows for the creation of hyper-realistic digital color maps. These maps are used to generate the most accurate possible virtual reconstructions of the figure's original, vibrant appearance, a form of non-destructive restoration that preserves the figure's true history without physically altering the fragile artifact. The digital conservator also plays a vital role in documentation and democratization. The high-precision 3D models and the extensive AI-generated data, the clay chemistry, the tool mark maps, and the organizational charts are all integrated into a central digital archive. This archive ensures the permanence of the data and provides universal access for researchers globally, fostering collaborative, worldwide effort in the preservation and study of the Terracotta Army. The digital conservator is thus a comprehensive system that ensures the survival and continuous study of the figures. It is a necessary answer to the ethical dilemma of preservation versus discovery, proving that the integration of AI is the ultimate safeguard for this ancient wonder, turning the fragile, 2,000-year-old army into a robust, eternally preserved digital asset for all of humanity. Among the four main subterranean vaults discovered near the mausoleum, Pit 4 presents a unique and profound mystery. It is the unfinished pit, a vast, 60-meter-long chamber that contains only the structural framework of the planned formation, devoid of the thousands of terracotta figures it was meant to house. This empty cavern stands as a powerful, silent testament to the tumultuous end of the Qin dynasty, forcing archaeologists and AI alike to determine why Pit 4 was abandoned by the builders and what this incomplete section reveals about the timing and priorities of the Imperial project. The physical evidence within Pit 4 is compelling. The chamber was prepared to the exact specifications of the other pits, featuring earthen partitions, packed floors, and the remains of timber support beams that would have once held the roof. The foundations for figures, the prepared clay base upon which the feet of the terracotta soldiers would have been affixed, are clearly visible, indicating that the construction was structurally complete and ready for the final, crucial stage of soldier placement. Yet, the figures themselves, which should have numbered around 1,000, are absent. The chamber holds only a few scattered tools, a small number of terracotta fragments, and most significantly, no organized ranks of soldiers. The primary archaeological hypothesis suggests that construction was violently halted shortly after the death of the first emperor in 210 BCE. His death triggered a rapid succession crisis, followed by widespread revolts across the newly unified empire. The massive labor force conscripted for the mausoleum, numbering hundreds of thousands, was quickly diverted to suppress the burgeoning rebellions or simply fled the imperial works. The abandonment of Pit 4 would thus represent the moment imperial authority collapsed, demonstrating that the final, glorious flourish of the emperor's eternal guard was sacrificed to the immediate needs of a dying dynasty. The AI analysis brings a quantitative lens to this historical interpretation. By analyzing the material science of the Pit 4 structure, specifically the chemical composition of the remaining clay fragments, the tool marks on the timber supports, and the packed earth of the floor, the AI is establishing a definitive timeline of construction. By comparing the unique mineral signatures of the clay foundation in Pit 4 to the clay used in the last completed sections of Pit 3, the algorithm can calculate the minimal time lag between the pit's structural completion and its abandonment. This helps verify the speed with which the empire imploded following the emperor's death. Furthermore, the AI is modeling the logistical deficit caused by the abandonment. By utilizing the tactical models derived from the completed pits, Pit 1, 2, and 3, the AI can predict the exact type and number of figures, infantry, archers, cavalry, that were scheduled for placement in Pit 4. This analysis reveals the intended function of the unfinished unit. The model suggests that Pit 4 was likely intended to house an essential elite unit, potentially a reserve force or a specialized unit of light infantry, rather than a main battle formation. The sudden absence of this elite force in the Eternal Guard's ranks underscores a panic and organizational chaos that must have gripped the Imperial works during the final collapse. The unfinished pit is thus a priceless historical document, a negative space that speaks volumes about the tumultuous transition from the absolute power of the first emperor to the complete organizational failure of his successors. It is the final material proof that even the most immense and meticulously planned project of eternity could be abruptly terminated by the swift, irreversible forces of political and social upheaval. The AI's ability to precisely date the structural components and model the intended troop deployment transforms the empty chamber into a highly active, informative historical scene, frozen at the very moment of dynastic collapse. The terracotta army pits, spectacular in their preservation, also bear the scars of violence and disruption, providing a complex damage report that is now being deciphered through AI analysis of looting and destruction patterns. While Qin Shi Huangdi was buried to preserve his empire for eternity, the immediate aftermath of his death saw his elaborate resting place become a target of political retribution and greed. The sheer extent of the destruction, the shattering of thousands of figures and the burning of the entire timber roof structure, has long been attributed to one primary source: the forces of Xiangyu, a major rebel leader who famously sacked the Qin capital and is historically blamed for the widespread destruction of the mausoleum complex shortly after 206 BCE. The AI's role in this historical detective work is to move beyond the singular, human-written narrative of blame and quantify the multiplicity of destructive events that must have occurred over centuries. The analysis begins with geometric fracture pattern mapping. Every shattered figure is digitally reconstructed, and the AI analyzes the force and directionality of the impact necessary to create the observed fracture patterns. By examining thousands of individual fractures, the AI can distinguish between destruction caused by the collapse of the roof structure, which would apply uniform, compressive force from above, and destruction caused by human-driven violence, which would involve localized lateral force, such as the strike of a blunt weapon. The analysis confirms two distinct phases of destruction. The primary destruction, the massive shattering of thousands of figures, aligns with the sudden and violent collapse of the massive timber roof beams, likely caused by a deliberate fire set by looters. The AI models a collapse in fire's intensity, confirming the scale of the human action required to ignite and sustain a blaze hot enough to cause such comprehensive structural failure. The second, more subtle phase revealed by the AI is the pattern of weapon theft. Historical accounts confirm that the terracotta figures were interred with real, fully functional bronze weapons, crossbows, spears, and swords, a priceless arsenal. The AI's spatial analysis reveals a statistically non-random distribution of weapon absence within the pits. Areas where the figures were most easily accessible following the collapse show a near-total absence of bronze weapons, suggesting systematic looting by a large, organized group that knew exactly where to search and how to strip the figures of their valuable armament. Crucially, the AI is searching for evidence of earlier, internal disruption. By analyzing precise sequencing of the construction and the damage layers, the algorithm seeks to find evidence of insider looting or sabotage that may have occurred during the 40 years the mausoleum was under construction. Such activity, which would have been rigorously suppressed by the first emperor, might manifest as subtle, localized damage or discrepancies in the figure's placement that predate the major collapse. The AI's damage report is transforming the understanding of the site's post-construction history, confirming that the army was not merely left to decay, but was actively and violently dismantled. It provides definitive, measurable evidence that the destruction was a complex, multi-stage event involving a massive fire, systematic looting of the priceless bronze arsenal, and a total collapse of surrounding structures, a complete, violent repudiation of the first emperor's claim to eternal dominion over his vast, silent guard. The Terracotta Army and the entire 70-square-kilometer mausoleum complex represent the apex of Qin Shi Huangdi's administrative power, but also the devastating human cost of his ambition. The documentary must delve into the reality of labor, logistics, and the empire's burden, the unseen, massive network of human suffering and resource allocation required to build a city for the dead. Historical records, notably Sima Qian's accounts, cite a staggering figure. 700,000 conscripted workers were forced into service over the 40-year construction period of the mausoleum. This immense labor force included highly skilled artisans, architects, engineers, and, overwhelmingly, unskilled laborers, convicts, and conscripts drawn from across the newly unified empire. The sheer scale of this deployment required a logistical effort that must have placed an unprecedented and ultimately unsustainable burden on the Qin economy and infrastructure. The AI is now providing a quantitative dimension to this human cost by modeling the resource consumption and logistical flow of the project. By using the AI-verified data on the clay chemistry, the algorithm can estimate the total volume of clay sourced from various geological locations and calculate the manpower and transportation resources required to extract, process, and transport those millions of tons of clay to the kiln sites. Similarly, by inputting the AI-verified data on the bronze weapon inventory and the extensive system of accountability, the algorithm can model the labor hours and industrial capacity required to smelt and forge the thousands of highly standardized bronze weapons, tracing the complex supply chain back to the copper and tin mines. The models confirm that the mausoleum construction was not simply a large project. It was the single most resource-intensive enterprise in the empire for 40 years, systematically draining manpower and materials from other crucial infrastructure projects like road construction and the Great Wall. The human cost is also investigated through osteological and anthropological evidence found in burial pits within the complex that contain the remains of workers who died during construction. While the full extent of this evidence is still emerging, the analysis of skeletal remains and mass graves reveals evidence of malnutrition, disease, and severe physical trauma, a physical testament to the harsh conditions under which the conscripted labor force toiled. The AI, by cross-referencing these anthropological findings with the project's logistical demands, can calculate the mortality rate and model the required labor replacement rate necessary to sustain the 700,000 worker population over 4 decades. This provides a cold, numerical estimate of the true toll the emperor's ambition exacted on his people. Furthermore, the burden on the Qin administration is highlighted by the AI's analysis of the system of accountability. The need to rigorously track the work of every artisan and maintain a complex, quality-controlled assembly line across decentralized workshops required a massive, dedicated bureaucracy. The success of the Terracotta Army is a measure of the Qin state's control, but the collapse of the project immediately following the emperor's death is a measure of the system's fragility. The AI's logistical models confirm that the complexity and scale of the mausoleum project stretched the young empire's administrative and economic resources to the absolute breaking point, suggesting that the construction of the Eternal Guard was a major contributing factor to the dynasty's swift and violent collapse just a few years after the first emperor's death. The final lesson of the army is that the staggering scale of the first emperor's ambition was ultimately its own undoing, draining the resources and goodwill necessary to sustain his empire in the living world. While the Terracotta Army has captivated the world, the vast majority of Qin's Shi Huangdi's mausoleum complex remains unexcavated, presenting a tantalizing mystery that is now being tackled through AI prediction of unexcavated chambers. The 60-square-kilometer complex is a highly structured, organized city of the dead, a perfect target for predictive computational archaeology. The AI's task is to analyze the existing data, the known distribution of the 4 main pits, the location of the inner and outer perimeter walls, and the position of various accessory pits containing acrobats, musicians, and bronze chariots, to map the underlying organizational logic of the entire necropolis and predict where other critical chambers are most likely located. The analysis relies on spatial modeling and pattern recognition. The AI first uses satellite imagery and non-invasive geophysical surveys, such as ground-penetrating radar and magnetometry, to detect anomalies beneath the Earth. This raw survey data, however, is often noisy and ambiguous, showing thousands of potential anomalies. The AI filters and prioritizes these anomalies by applying known Qin administrative and military patterns. For example, the algorithm knows that the army pits are organized around the east-facing defense perimeter, while the pits containing entertainers and administrators are organized closer to the central, unexcavated tomb mound, mirroring the structure of the imperial court. The AI uses this established pattern to assign a high-probability score to unexcavated anomalies that conform to the known imperial logic. A key area of predictive interest is the presumed location of the administrative and civilian bureaucracy. The terracotta figures found so far represent the military, and the court's periphery musicians, acrobats. A complete shadow empire would necessarily include the central administration, figures representing chancellors, scribes, ministers, and tax collectors, the vital civilian organs of the Qin state. The AI is modeling the logical, symmetrical placement of these administrative pits relative to the central tomb mound and the known military pits. An anomaly exhibiting the correct size and positioning to house a full terracotta bureaucracy is assigned a much higher priority for future excavation. Another crucial predictive target is the logistical supply areas. Based on the AI's analysis of the massive logistical effort required, the algorithm is modeling the most likely locations for storage pits containing materials, tools, and perhaps even the remains of unutilized standardized body parts. The existence of these pits would provide invaluable material evidence for the AI's theories on modular construction and mass production. The AI's prediction is not a final answer, but a powerful roadmap for future archaeological fieldwork, saving thousands of hours of unnecessary digging and focusing limited resources on the anomalies with the highest probability of revealing new, structured pits. The application of AI has transformed the exploration of the mausoleum from a physical search into a mathematically guided investigation, ensuring that the next major discovery will not be accidental, but calculated, data-driven revelation of the first emperor's complete eternal shadow empire. The hidden city of the dead is finally beginning to reveal its secrets, one predicted chamber at a time. The immense artificial earthen mound marking the burial site of Qin Shi Huangdi is the unseen tomb, the profound, unexcavated center of the entire mausoleum complex, and the ultimate repository of the first emperor's secrets. While the Terracotta army sits 1.5 kilometers away, the central tomb mount itself remains sealed, protected by a combination of reverence, fear of destroying unique historical material, and the persistent historical warnings of its formidable defenses. The greatest of these warnings comes from the ancient text describing a massive, intricate subterranean palace, featuring rivers and lakes of liquid mercury and mechanical crossbows rigged to fire upon intruders. Scanning the Emperor's final palace is the non-invasive, high-stakes investigation aimed at mapping the tomb's internal structure without breaching its integrity. Direct excavation is currently deemed too risky due to the high probability of irreversible damage to the unique artifacts and, crucially, the unknown effects of exposure to potentially massive quantities of elemental mercury. Non-invasive geophysical surveys are therefore paramount. The AI is deployed to process and interpret the data gathered by magnetometry and seismic surveys. Magnetometry measures tiny variations in the Earth's magnetic field, allowing researchers to detect buried structures made of fired earth, like kilns or brickwork, or large concentrations of metal, such as bronze weapons, chariots, or the massive quantities of iron that would have been used in the tomb's infrastructure. Seismic surveys use controlled low-frequency vibrations to map subterranean structures based on how the waves reflect off different materials, allowing researchers to distinguish between loose soil, packed earth, and the dense, compressed chambers that would house the inner palace. The AI's role is to filter out the geological noise and identify patterns consistent with the historian Sima Qian's account. For example, the AI is looking for patterns in the magnetometry data that correspond to high concentrations of metal in the central area, potentially confirming the presence of bronze artifacts or the massive architectural components required to support a subterranean palace. Most compellingly, the AI is used to verify the legends of the Mercury rivers. By analyzing the chemical signatures in the soil directly above the tomb mound, scientists have confirmed extremely high concentrations of elemental mercury, concentrations significantly above background levels. While not conclusive proof of flowing rivers, the AI models the distribution and spread of this mercury vapor, providing strong evidence of a massive, confined source of the toxic element within the tomb chamber itself, validating the ancient texts and confirming the formidable nature of the final palace's defenses. The final goal of the AI scanning is to produce a definitive three-dimensional structural blueprint of the unseen tomb's internal architecture. This map would detail the location of the Emperor's sarcophagus chamber, the supporting walls, the entrance ramps, and, crucially, the placement of any potential defense mechanisms. This digital investigation provides the necessary knowledge to plan for eventual, safe excavation decades from now. The unseen tomb remains the ultimate mystery of the mausoleum, a challenge that requires the highest level of technological sophistication to penetrate the physical and mythological defenses of the emperor who sought to rule for eternity. The most formidable and infamous defense of Qin Shi Huangdi's central tomb, according to ancient texts, lies in the Mercury rivers, a legendary system of flowing, toxic liquid that form miniature rivers and lakes, designed to represent the waterways of his unified empire within his final palace. This story has long straddled the line between myth and historical fact, but modern science and AI modeling are now actively replicating the toxic defense grid to understand its function and formidable danger. The evidence of the Mercury rivers, as noted previously, is surprisingly robust. Scientific surveys conducted over the central tomb mound have revealed highly elevated concentrations of elemental mercury in the soil samples, concentrations that are hundreds of times higher than natural background levels. This discovery validates the core claim of the ancient historian Myste, who wrote that the mercury was set up to flow mechanically within the tomb to symbolize the great rivers and seas of the Qin Empire. The sheer quantity of mercury required for the symbolic endeavor would have been immense, sourced from the mercury mines of the empire and refined through a complex, dedicated industrial process. The AI is tasked with modeling the functionality and dispersal of this toxic defense grid. By inputting the estimated volume of mercury, the dimensions of the inner tomb chamber as predicted by seismic surveys, and the known chemical and physical properties of liquid mercury, the algorithm can simulate the ancient system. The simulation confirms that the mercury, besides its symbolic function, would have served as an incredibly effective, multi-layered toxic defense mechanism. First, the massive quantity of mercury would generate a lethal concentration of mercury vapor within the sealed tomb chamber. This vapor, colorless and odorless, would have instantly incapacitated and killed any unauthorized intruder breaching the inner sanctum, ensuring that the emperor's remains and treasures were protected not by simple stone and soil, but by an inescapable chemical trap. The AI modeling helps calculate the rate of vaporization and the time required for the chamber to become lethally saturated. Second, the flowing nature of the mercury rivers, whether activated by mechanical means or merely remaining in a liquid state, suggests a system of perpetual deterrence. The toxic liquid was likely designed to flow and pool, protecting the central sarcophagus and ensuring that the inner palace will remain an uninhabitable, chemically hostile environment for any subsequent plunderers, maintaining the emperor's eternal solitude. The replication of the toxic defense grid through AI modeling allows researchers to understand the sophistication of Qin engineering and its chemical warfare capabilities. It confirms that the first emperor's vision for his mausoleum was not just about grandeur, but about ultimate security, employing science and materials that were both symbolically rich and lethally effective. The terrifying legend of the Mercury Rivers is no longer a myth. It is a scientifically confirmed, functioning toxic defense grid, the most dangerous and enduring secret of the unseen tomb, reinforcing the need for extreme caution and non-invasive scanning before any future excavation is even considered. Despite the revolutionary breakthroughs achieved through data-driven analysis, the study of the Terracotta army still confronts the enduring reality of the AI's challenge, the recognition of what can never be reconstructed, and the permanent gaps in our historical knowledge. The sheer age of the figures, the destruction wrought by time and human hands, and the limitations of the historical record mean that certain dimensions of the first emperor's vision are forever lost to us. The most profound and irreversible loss is the original subjective life and atmosphere of the mausoleum. The figures were once painted in brilliant, dazzling colors, their armor gleaming, their bronze weapons polished to a dangerous sheen. The pits were sealed by a colossal timber roof that would have created an oppressive, immense chamber. The soldiers would have stood not in the muted gray-brown of baked earth, but in a vibrant, almost overwhelming display of imperial power. While AI can digitally reconstruct the color palettes and model the geometric organization, it can never restore the sensory experience. The smell of the lacquer, the sounds of the immense silence under the earth, or the emotional impact a completed project would have had on the original builders. This is irrevocable loss of atmosphere, an effect that no algorithm can ever retrieve. A second, profound challenge is the identity of the unrepresented. The figures excavated thus far represent the military, the entertainers, and some court officials. But the vast, unexcavated accessory pits in the central tomb itself would have held figures or artifacts representing the emperor's entire living world. His family, his concubines, his political rivals, and his most trusted advisors. The total destruction of the records that detailed the full inventory of the mausoleum means that the true cast of characters in the emperor's afterlife is forever incomplete. The AI can predict the location of the administrative pits, but it can never retrieve the historical narrative of the people the figures were intended to represent. Furthermore, the final, fatal loss is the specifics of the destruction. While the AI can map the patterns of fire and looting and attribute the destruction to large-scale events, It can never retrieve the intent of the looters, the specific details of the collapse, or the full, emotional story of the final days of the mausoleum construction and subsequent abandonment. The AI's challenge is ultimately one of humility. The machine is a perfect tool for solving quantifiable problems, geometry, chemistry, and statistics, but is powerless before the great subjective, unquantifiable forces of history, human emotion, political intent, and the sensory experience of a moment 2 millennia gone. The digital resurrection brings us closer to quantifiable truth, but it must coexist with the enduring recognition that the silent guard of Qin Shi Huangdi will always retain a powerful, core mystery that is permanently beyond the reach of any algorithm. The incomplete nature of the army is not just an archaeological problem, but a reminder that history is always a fragmented, partially lost narrative. The application of artificial intelligence and high-resolution scanning to the Terracotta army, the use of technology to solve ancient mysteries, introduces a critical ethical dilemma concerning preservation and the past. This dilemma centers on the responsibility of modern researchers to interact with unique, fragile, and irreplaceable cultural heritage, balancing the imperative for discovery with the solemn necessity of long-term conservation. The primary ethical concern revolves around intrusive data collection. While the 3D laser scanning itself is non-invasive, the need for the AI to analyze subtle data requires researchers to physically handle and manipulate the fragile figures for scanning, potentially accelerating the decay of pigments or destabilizing cracks. Furthermore, the necessity of obtaining material evidence, such as the small samples of clay required for chemical analysis, inevitably involves a degree of destructive sampling, where a microscopic piece of the original artifact is sacrificed for scientific data. The ethical mandate is to establish rigorous protocols to ensure that the data gain significantly outweighs the minimal necessary physical cost, requiring international consensus on the acceptable thresholds of sample size and handling time. A second, more complex dilemma involves digital permanence and access. The AI-generated 3D models and massive datasets are essentially the digital twins of the Terracotta army, the primary artifacts that future generations of researchers will use. The ethical imperative is to ensure the long-term digital preservation of these complex files, migrating them across evolving technology platforms to prevent the data deluge itself from becoming obsolete. Furthermore, the question of access is crucial. Should these digital twins be fully open to researchers worldwide to maximize historical insight, or should access be restricted to protect the intellectual property and sovereignty of the host nation? The use of AI, a technology often developed in private, commercial labs, also raises questions about the commercialization of cultural heritage and the need for public benefit over private profit. A third ethical consideration centers on the interpretation and narrative. The AI, by providing statistically definitive answers to questions of production and logistics, possesses the power to reshape the historical narrative, challenging decades of human-derived archaeological theories. The ethical responsibility of the archaeologist is to ensure that the AI's conclusions are always presented with transparency, rigorously tested, and integrated carefully into the broader historical and cultural context, avoiding the pitfall of technological determinism, where quantitative data eclipses humanistic insight. The ethical dilemma of the Terracotta Army study is a microcosm of the challenges facing all digital humanities projects. It demands a new, heightened level of responsibility from researchers to govern the interface between ancient material culture and cutting-edge technology, ensuring that the pursuit of new knowledge does not compromise the sacred duty of preservation, and that the history revealed by the machine remains ethically accountable to the human story. The application of artificial intelligence to the silent guard of Qin Shi Huangdi has created a profound living legacy, demonstrating how AI is changing ancient history and reshaping the discipline of archaeology for the 21st century. The success of the Terracotta Army project serves as a definitive case study in computational archaeology, establishing new paradigms for how researchers worldwide interact with complex, large-scale historical datasets. The primary legacy is the establishment of a new standard of evidence. AI moves historical claims from the realm of subjective inference and visual comparison into the realm of statistically validated proof. When the AI confirms that a specific style of ear belongs to one of 5 core templates with a 99% confidence score, that finding is no longer an archaeologist's hypothesis. It is a scientifically robust conclusion about ancient industrial practice. This new standard encourages a level of rigor and objectivity previously unattainable in the humanities, transforming archaeology into a truly data-driven science. A second crucial legacy is the concept of holistic analysis and systemic thinking. Traditional archaeology often focuses on individual artifacts or specific trenches. The AI, by necessity, demands a systemic view, forcing researchers to consider the entire Terracotta army and mausoleum complex as a single massive, integrated system. The ability to correlate material science, clay chemistry, geometry, armor patterns, and historical documents, inscribed marks, demonstrates that the most complex historical truths are often found at the intersection of multiple, previously separated datasets. This holistic approach is now being applied to other global sites, from the study of Roman legions to the analysis of Mesoamerican urban planning, fundamentally changing the scale at which historical questions are asked. Furthermore, the AI's success creates a living digital resource. The high-resolution 3D models and digital datasets are themselves a living legacy, a research resource that is accessible globally and can be continuously updated and analyzed by future generations of scholars using technologies not yet invented. This democratizes the study of the Terracotta army, ensuring that the work is not confined to a single team, but becomes a global, collaborative effort. The AI is thus changing ancient history not just by revealing new facts, but by changing who can participate in the discovery and how those discoveries are verified and preserved. The living legacy of the plywood fandom is the proof that the biggest challenges of the past, the challenges of scale, fragmentation, and complexity, can now be overcome by the analytical power of the machine, ensuring that the silent records of ancient empires will continue to speak with clarity and statistical certainty for centuries to come. The future of history is no longer just about digging up the past. It is about digitally reconstructing, analyzing, and preserving it for an eternal research future. The ultimate story of the Terracotta army is the enduring riddle of Qin Shi Huangdi, a historical puzzle that has been fundamentally reshaped by the relentless, quantitative logic of artificial intelligence. The army, once a static symbol of ancient power, has been digitally resurrected, analyzed, and functionally reverse-engineered, yielding secrets about the Qin dynasty's industrial capacity, military organization, and administrative control that were inaccessible to previous generations of archaeologists. The primary revelation of this entire undertaking is that standardization was the secret to the empire's grandeur. The unique face, once believed to be a portrait of an individual soul, is now understood to be the result of a brilliant, modular mass production system, a sophisticated illusion of individuality built upon a foundation of standardized, interchangeable parts. The AI-verified clustering of facial geometry, the analysis of armor patterns, and the tracing of the supply chain through clay chemistry all confirm that the Qin state was a master of logistics and industrial efficiency on a scale previously unimaginable for 3rd century BCE. This massive logistical system, however, held the seeds of the empire's own destruction, confirming that the very burden of creating this eternal guard contributed significantly to the swift collapse of the dynasty shortly after the emperor's death. The AI modeling of the unfinished pit and the intense logistical demands confirmed that the project was a drain of unsustainable human and material resources. The ultimate legacy of the entire mausoleum is thus a powerful duality. It is a supreme testament to the emperor's genius for unification and control, and simultaneously, the clearest evidence of the fatal fragility that lay at the heart of his hyper-centralized, resource-draining empire. The enduring riddle, therefore, shifts from how the army was made to what the army means for nature power. The AI has quantified the geometry of control, but it has not explained the madness of the ambition. The investigation into the Terracotta army stands as a profound moment in the history of archaeology, proving that the deepest understanding of the past now requires the most advanced technologies of the present. The AI has solved the riddle of production and logistics, but the greatest mysteries, the content of the unexcavated central tomb, the truth behind the Mercury rivers, and the identities of the 700,000 conscripted workers remain sealed beneath the earth. Directed to a new generation of scientists, engineers, and historians globally, the work must continue, but it must be guided by the lessons learned, rigor, collaboration, and ethical preservation. We call for a global initiative to digitize and analyze other complex, large-scale archaeological sites across the world, applying the proven methodology of the Terracotta Army Project to unlock similar systemic secrets in other ancient civilizations. We need to recruit a new cohort of computational archaeologists, individuals fluent in both historical research and machine learning, to lead this new era of discovery. Furthermore, we call for international, open-source collaboration on the Terracotta Army's digital models. The sheer volume of data demands that researchers from all nations possessing specialized knowledge in different fields, from ancient metallurgy to computational fluid dynamics, work together to fully exhaust the potential of the digital twin. The future of the past cannot be the work of a single nation or a single discipline. The final and most crucial call is for preservation through data. The AI has shown that our best defense against the irreversible decay of time and the destructive forces of nature is the creation of perfect, accessible digital records. By investing in hyper-resolution scanning and long-term digital archiving, we ensure that the fragile figures of the first emperor's eternal guard will survive in digital form for all eternity, fulfilling the very ambition of Qin Shi Huangdi himself. The silence of the terracotta figures has been broken by the voice of machine. The time for the world to listen and to act on this profound new knowledge is now. The most powerful secrets of the ancient world are no longer hidden. They are simply waiting to be computed. The next great discovery is not in the ground, but in the code,